Well, good morning, everybody. Lovely to see you. I think if we were to do a genetic analysis, that many dementia researchers would be night owls rather than morning larks, which doesn't really bode well for their biological aging process. I must confess that I think most of us have been a bit, how can I put it, traumatized, wouldn't be too strong a word, by the fact that the biological aging can accelerate so fast in certain groups. So Cornelia, thank you so much for that. It was really, really encouraging. So my privilege this morning is just to welcome Chris Brunton. Please, Chris, come up. Chris was diagnosed about 5 years ago with MCI. Honestly, he's a very interesting person. Wonderful career. Was a teacher focusing on special needs. And he is here with his wife, Sue. And welcome, Sue. It's lovely to have you here. And Chris is going just to give a little bit of a background to his experience as somebody living with MCI. So, Chris, over to you.
Thank you. Thank you, John. Good morning, everybody. Apologies for me. I'm going to move this a little bit, sorry. Apologies for reading this, but it'll help fluency and hopefully the discipline of keeping to the subject and moderately to time that I'm allocated, I hope. For my contribution today, I'll begin with a little of who I am, the history that led to my diagnoses, and then to the many challenges they bring, and I'll finish with the opportunities that have arisen with my offering myself to research. Firstly, as a young teenager, I was active and adventurous. I walked the countryside, sailed, caved, climbed mountains, rock climbed, canoed, learnt bushcraft and how woodlands and forest help form the world, eventually gaining many qualifications and instructor certificates. I've always been an opportunist. I've never said no to an invitation. As a 16-year-old, I sailed the islands of the Aegean Sea, coping with storms and force 9 gales. Later in life, I sailed across the Atlantic on a square-rigged 3-masted bark, the Lord Nelson. In my 20s, with 2 friends on a 6-day mountaineering expedition in the Dolomitic Alps, I was avalanched and dug out by my friends. For a career, I surprised myself. I became a teacher. I thought I wanted to leave school, not go back in. But I found helping children with learning difficulties my vocation, and I did that for 33 of my 36 years teaching. However, early on, more opportunities came, and I qualified with a PCV license, and for a summer season, I drove coaches weekly to Yugoslavia, to a beautiful resort, Rovin, on the North Adriatic coast. Lost my way. MCI kicks in. I was invited to join a forestry gang in the Dyfi Forest, North Wales. I was asked to get myself a chainsaw. I was shown how to fell a 70-foot spruce tree, and then left to fell 40 trees a day for the timber industry. I was finally invited to become an instructor at Abu Dhabi Outward Bound School, where Kurt Hahn, during the last war, developed the concept of outdoor education. I retired eventually from full-time work in 2013, having finished my career teaching 30 years in a residential special school that became a day school, teaching art, pottery, heavy craft, and most significantly outdoor education, specialising in forest school. I was diagnosed with sleep apnea in 2016 because Sue was concerned that I was holding my breath at night, asked me to go down to the doctors, and I now permanently use a CPAP machine. Was this the first related condition to MCI? Who knows? Across 2018, I experienced perhaps 4 or 5 what were described as TGAs and TIAs, mini-strokes, later presumed by the consultant neurologist to be partial seizures, following a nocturnal tonic-clonic seizure, 3 a.m., that Sue found me seizing, not breathing, and had to give me 8 minutes CPR. So when the emergency services arrived, I was displaying a Glasgow coma scale of 3, described as totally comatose or dead. So now, to my first clearly related experience of MCI. I was shopping in Tesco's. A young lady in her 20s or 30s came skipping down the aisle, flung her arms around me, gave me a big kiss on the cheek and said, "Chris, how are you? Lovely to see you." Highly embarrassed, I felt I'd never met her before, didn't recognise her. I had to fudge my way through the greeting, smile, and just feel terrible as I left. That's one experience I'll never forget. I now catch myself talking to myself lots more. I stumble with my thoughts and words. I get more confused, as you can hear, with things that used to be straightforward, forgetting how I began a comment in conversation as I try to explain or describe things, not finding the right word. I stumble, I stall, and I hesitate. I'm easily irritated by daft, irrelevant, small things that have got nothing to do with me. I shouldn't have an opinion on why people have tattoos or hairstyles or fashionable clothes. Middle lane driving on the motorway. Oh, don't half annoy me that. Putting people putting their feet up on the train seat. No, you shouldn't do that. Inconsiderately taking up extra seats with their bags. I'd prefer that people helped each other around them, not just living selfishly, but I let it bother me. I know I've always been a bit self-opinionated, but now it's an exaggerated trait from younger years. I find myself working in my workshop or around the garden, making very quiet, breathy, whistling noises. It'll be just 2, 3, or 4 notes, and I'm repeating it and repeating it and repeating it over and over again. But when I become aware of it, I get really annoyed with myself. I tell myself off and I have to concentrate really hard to avoid it starting again, but not very successfully. Friends say, "But what's the problem? You're not hurting anyone." But I hate it. I sometimes feel really quite lost. I creep into myself, finding it much easier to keep my own company rather than make comments in conversation with a group or in company and then be corrected or contradicted. I get more and more forgetful. Lots of things that I've done in the past, what I'm doing now, where I've travelled, the hundreds of paths and lanes for Hertfordshire County Council that I've worked on with the Rights of Way team, the bridges, the gates, the fences I've mended, but now they just seem completely new terrain. Jobs that I've said to friends I'd do for them and then completely forgotten and not done at all. But then I can remember extraordinarily distant, minute, detailed things that I haven't thought of for decades and decades. I have hearing problems. I use hearing aids. It causes struggle to be clear in understanding, listening to being less interested in conversation. Leading to being less interested in conversation, despite being a sociable person who enjoys a chatter and banter. I've always been easily distracted from the task I'm doing, but it's becoming worse. I find it very difficult to remind myself what I was doing before, e.g., going out to my workshop to do a small job, and something else suddenly I notice needs doing, and I completely forget the original task. It will happen over and over again. It causes a very deep sense of frustration, ending up in extended periods of feeling very low, unmotivated, and I suppose ultimately depression. However, a few friends who are interested and want to understand and share a conversation about it, sometimes it can cause lots of fun. We can laugh even hysterically, but it's rare. Ironically, MCI gets me thinking lots. It makes me withdraw, therefore mull over my own thoughts. I spend lots of time now just with myself, questioning, is it me? Is it old age? Is it MCI? Or is it actually dementia in its early forms? I'm more often confused of things that used to be everyday things. I'm not pronouncing words properly. They're getting fuzzy, and it's happening more and more, and recently very much noticed by both me and Sue. I am, however, at the interesting stage of knowing that something's going wrong, but I'm uncomfortably aware that I can't easily correct it, if at all. I have a horrible lack of motivation. I've lots less energy, even less interest in doing things that I used to love doing. I turn bowls on the lathe, plates on the lathe. I do sculptures with my chainsaw. I make wooden toys for the grandchildren. Experience that I loved, I still remember well, but I'm not doing anymore. Being a qualified mountain leader for much of my life and long-distance continental coach driver for a little while, I'm now finding my navigational awareness and ability severely challenged. I'm less confident in the mountains, especially if the weather closes in and visibility gets significantly reduced, something I really actually used to enjoy and get excited by. I do go for walks, often down to town or out into the countryside, but I can get disorientated. I'm taking fewer bike rides. Why? Epilepsy and its drugs, levetiracetam, Keppra, play their part, but I'm not really sure how. Is this what makes me moody, lifeless, lazy, more critical of others and of myself? Really, really lacking energy, even sometimes feeling I've just had enough. I'll let you interpret that as you will. But be assured, I've never had suicidal tendencies. One of the challenges is getting used to the fact that it's actually here. It's real, it's not just a broken arm that will mend. It's the truth, and I've got to get used to it. But it's also very real for Sue, for the family, for friends who say, "Chris, how are you?" How do I answer that? I like to be an honest person. What do I say? I'm still otherwise reasonably healthy and reasonably happy. The DVLA still allow me a driving license, and in my own self-opinionated way, I'm afraid I think I drive a lot better and a lot safer than many other people on the road. And these are very big things to get used to. So, opportunities and research. How to turn a negative experience into a positive one. On diagnosis, I realised that this was possibly the beginning of something going much more deeply wrong. Dementia was never mentioned by any of the professionals treating me, and I've not had that direct diagnosis. I was keen to use my diagnosis of MCI to help others if I could. I went on the internet, I looked for research organisations, and I was invited to join Great Minds. I took part in some Zoom meetings. I attended a conference in Oxford, and then in the Imperial College in June last year. Dr. Ivan Koichev's team asked me if my details could be passed to the Bristol Brain Centre, and they introduced me to their coordinator, Julie Clayton. Many of you might know her. The Remember group, the research into memory, brain and dementia, is the one that I'm active with, but she's an incredible lady, and she coordinates about 10 different research groups. I was invited to join as a PPI member, and they've kept myself and many other participants incredibly busy on many, many newly proposed research projects, grant applications, research training projects for PhD students, all really interesting and forward-seeking projects. It's really excited me. I feel very, very privileged to be invited to contribute this way, and frequently, sometimes twice or 3 times a week. I'm also incredibly grateful to be given the opportunity to join you in your work. So thank you for inviting me to participate today. And if I can be of any further help to you, or you want to know more, I'd really appreciate being approached. I wish you all truly positive and far-reaching results in the projects you and your research that you take on. But lastly, opening my notebook just to scribble down a few thoughts for today, a couple of little leaves dropped onto the floor. I picked them up. I noticed John Gallagher's name at the top of them. These are the few of the thoughts that I'd noted. To maintain good cognitive health, be happy, do things to help others, be generous, don't carry anger, do get justice, but forgive. Be honest with yourself. Sadness is how to detach from emotion, a good support and value, but try not to stay unhappy for too long. Give compliments. Giving means receiving, not taking. Don't get bored. Do something about it. As far as cognition is concerned, use it or lose it. Do more exercise, more activity, play games, things you enjoy. Be happy. Thank you, John.
Wow, somebody remembered something I said. Well pleased with that. So Chris just helps us remember why we're here. Okay, and I think, amongst all the really stimulating cut and thrust of academic and industry life, the whole point here is to develop treatments and early detection and treatments for people like Chris, and apparently not too far away for people like us. Okay, so it's my great pleasure now to welcome Simon, who leads our big data team. He is the clever person behind all our informatics. So Simon, off you go.
So thank you, Chris. It was really good to hear your perspective. So I'm a technologist specializing in research infrastructure. So I rarely get out in the real world, and I sure as hell never real people. So it's great to know why we get out of bed in the morning. I just want to talk about big data. Now, big data is nothing new, but it's an evolution. If you go back 5 years, we were all just trying to find data, collect data, put data together. The introduction of the FAIR principle came in to kind of really drive the agenda of like trying to get data together. But I think, at last year's conference, we really majored on the maturity of the ecosystem, the fact that we had moved on, we had grown up, we have data. We majored on multimodality data and the fact that we can combine these together. And I think, again, last year we spoke really about getting the best people to do the best science from anywhere that they can. And I think that was the real motivation of the last conference. But I think we're on the next evolution now. We've really moved on. The challenge now really is to utilize that data, to make it usable, to really drive the science, drive the discovery, and to really break down barriers going forwards. So an example of this is the DPUK has, for instance, in neuroimaging, really taken a massive evolutionary leap. The whole process of submitting neuroimaging data and checking it and anonymizing it and standardizing it into the same format. The guys and girls that work on this, they take the images, they remove the face, which is a bit freaky, from the image to keep the identity of the individual safe. But they also standardize the data into a common data model. And therefore, we've seen a number of examples of scientists come along now and write their algorithm, write their science across all of the cohorts without having to repeat it and change it on every single cohort. And this is showing that the upfront effort of aligning the data is worth it because the output is massive. We're also working on AI is obviously the next major evolutionary step. Working on synthetic data to remove bias from the AI models and all of those sort of things. So there's a lot going on there. And this is the work from Lewis, who's over there. This is the pipeline, if you like, for cleaning the data and sorting the data out. And I think this is really important that we share these sort of pipelines because the effort needed to build this is huge. But also, when we process the data, we really need to start being aware of the carbon impact of what we're doing. It takes a lot of compute resource to kind of do this. So once we've done it, let's share it at every conceivable stage. But we're also going beyond this in the sense that there are now also the biobank image-derived phenotype workflow is on there and 2 others. And this is representing that actually if neuroimaging is not the thing that motivates you to get out of bed in the morning, Can we turn one modality into another modality and allow you to still capitalize on the great science that's happening in the modality over there? Another example is led out of our colleagues in Cardiff University. We're now systematically producing polygenic risk scores on all the genomic data. But again, you can either have the genomic data and do it all yourself, or again, you can capitalize on the work of others. And I think going forwards, we need to really push the whole building science on top of science on top of science. And maybe in the infrastructure world, we've not really embraced it like you have in the academic world. And I think it's time for a bit of a shift here in the way that we approach these and approach this problem. To that point, DPUK has recently joined the Alexia network, which is a pan-European network of bioinformaticians and genomic-related folk. And again, it's part of let's find the right people with the right knowledge to collaborate with. Let's not reinvent the wheel all the time. Let's form strategic collaborations with these groups so we can kind of bring the best of breed and the best capabilities to our scientists. And through HGRUK, which has formerly formed a relationship with Global Alliance for Global Health, we are also therefore interconnected with that community, which is obviously a worldwide genomic initiative. And this is only now 6 months old, this relationship, but we're really pushing to capitalize on the fact that we must learn from others and we must accelerate the delivery of science, and that big data should not be a barrier. The big part of it, perhaps over time, will go away. We'll stop calling it big data, we just call it data. Because if we can handle data of any size, of any modality and any data type, this is what we need to, this is our aspiration to get to. However, the world has gone a bit crazy, and everyone in the world is building their own trusted research environment. This is great fun for me as someone who spent their entire professional career building these things, so I get to have some really interesting conversations. But there's some really crazy ideas out there, and I think there's a lot of fun going on. But we're not innocent here. So DPUK is also being a bit disruptive to the market going forwards. So DPUK now has trusted research environments inside trusted research environments. So 2 motor neuron disease trusted research environments are inside DPUK, traumatic brain injury trusted research environments inside. And although they're taking a bit more time to mature, the stem cells and the tissue TREs are there, but obviously they're collecting samples and building themselves up. This is recognizing that actually the art and science of building trusted research environments is a distraction from doing science. And actually, if we can capitalize on all of the work that DPUK is doing to do data management and governance and security and safety and all that good stuff, that allows these groups to start with science on day one and inherit all of that necessary evil in order to kind of facilitate a platform going forwards. But we are in a new era, ironically. We've liberated all the data, and across the UK particularly, we are trying our very best to lock it back up. So we are possibly heading in for a new problem going forwards. The data is actually going to accidentally become siloed as a consequence of everybody trying to kind of move to the new model of working. And obviously, it doesn't really matter if you have to access one TRE to do some science and then another one, and you combine the data, and then you combine the results. But increasingly, we're going to find that half the data is in one TRE and half the data is in the other. And this is going to be a new problem. It's not a problem today as such, but it definitely will be a problem in the next year or 2 years. So as such, DPUK has had a long-term relationship with ADDI Workbench since its inception. We've always been a key partner with this initiative. We've always contributed in every single way that we can. And what this initiative done, which is a many-year initiative, is really push the boundaries of federated data access. It was slightly before its time in the sense that it's been a difficult trip because we've had to realign our thinking, realign governance, and realign all of these aspects. But as a collective, we've become pushing forwards on this for a number of years, and we're now in a very good state. But to respond to this problem, DPUK and the work of my department is really pushing forward with ADDI and Health Data Research UK and DARE UK and Elixir and J4JH and the UK Trusted Research Environment and Community. SDEs, if you're not familiar, is a Secure Data Environment. It's NHS England's new acronym for the same thing, bless them. But so what we're doing is we're driving the evolution of this technology. We need this technology to almost go away from you data scientists and you researchers. the plumbing needs to become just something a bit like the power network in the UK. It needs to become invisible, and that we need to make sure that we can combine the data together so that you can effectively do the science that you need to do to help people like Chris and others and to find both therapies and hopefully a cure over time. So trusted research environments are definitely maturing. AI is the next big endeavor, and AI-ready data sets is the new cool theme that everybody gets excited about. But trusted research environments do this all day, every day. This is basically, can we harmonize the data? Can we clean the data? Can we summarize the data, profile the data, describe the data, shape the data? This is what TREs do all day. And I guess so to us, we don't really know what all the fuss is about, but I think we need to work with the AI community to kind of make sure that we are providing half of the picture, effectively doing our bit ready so that the AI folk can again focus on the science of doing AI and not the science of data management and data preparation and so on and so forth. Obviously, big data is a prerequisite for AI. I think we've got a lot of this, and I think this is really driving one of the agendas to kind of, let's use that data, let's push the boundaries of what we can get from that data. We do think that, as this evolves, it was mentioned yesterday, DPUK is just about to release a report. I think it goes out in the next few days about how do we release AI models on sensitive data from a trusted research environment. Because as we build more and more AI models, if they are kept siloed, then what is the point? What is the benefit to society? If we can do AI models and we can release them and other people can take those AI models and use them, or take those AI models and build upon them, then this is the only way that we're really going to get the snowball effect and kind of get, a sum bigger than the parts. But there are inherent risks in doing this, but we don't say no, we just need to find how to say yes, and we're working really hard on that. So in conclusion then, I think we have big data. Perhaps next conference, we drop the word big, it's just data. We know how to handle it securely, this is not a problem. But I think we almost have a public responsibility now to really drive the use case and the public benefit of using that data, and stop making excuses why we can't share it, why we can't do it. These are all nonsense. They can all be solved. We just need to frame whatever it is has to be done. What is the barrier? Where are you setting the bar? And we'll meet the bar. It's not a problem. All data is not born equal, of course. I'm not being naive, but everything can be solved if we have enough will and we have enough desire to do this. So I'll stop speaking here because we have some fantastic speakers today. They will introduce themselves and their bios in the documents in front of you. But we have, starting off with two international rock stars, effectively, Professor David Bennett and Professor Haraldsen, bringing their international perspective, which I'm really interested in hearing. And then we move on to our UK colleagues, both bringing, so Dr. Robin Wolz brings the angle from industry, although he's an academic, he's lived in industry throughout his professional career. Again, it's important that we bring that perspective, and that perspective is heard nice and loud. And then Professor David Llewellyn, again, will bring an academic perspective. And then once we've enjoyed their speeches, we then move on to two fantastic early career researchers, Ben from Sheffield University and Danielle from Oxford University. And it's important that we give these sort of people the space, because they're the future. Effectively, one day we'll all retire, and we will need these people to basically solve the problem for us. So David has been here for 36 hours. We've really enjoyed his company. However, as soon as he's finished his talk, he has to jump on a plane and go back and do great science in America. So the program will be slightly changed. We'll ask David to give his presentation, and then we'll ask questions immediately to enable us to really interrogate David and then allow him to jump on a plane and unfortunately go back to the wrong country. So, David.
Good morning. It is morning, right? Yeah, morning someplace. It's really a pleasure to be here. I've been here 24 hours so far. And I just want to talk about embracing complexity. This is a topic John and I discussed And I think it's fitting for this group here. Okay, I want to thank my colleagues at the Rush Alzheimer's Disease Center in Chicago and across the country that participated in the data I'm going to share today, and acknowledge our funders, the remarkable study participants that have been with me for over 3 decades now, some of them, and I have no relevant disclosures. And the motivating questions are quite simple, and that's where we started over 3 decades ago. Why do older people lose cognition as they age? And then how can we find therapeutics to treat, and more importantly, to prevent Alzheimer's disease and related disorders in older persons? So I started 2 clinical pathologic cohort studies of aging and Alzheimer's disease. And the first one is called the Religious Order Study. This started in 1994. Over the years, we've enrolled more than 1,500 older nuns, priests, and brothers. They enroll without known dementia. They agree to annual clinical evaluation, annual blood donation. Over 400 have developed new onset incident dementia. Over 600 have developed new onset incident mild cognitive impairment. And we have about 950 brain autopsies. Welcome to America here. Here is Chicago, which is where I'm based. And we work with across 15 states in the United States. We work with about 35 different groups. And I send a team that flies out or drives out, depending, to all of these places to enroll people, to test people. We branched out to a lot of male orders and female orders. We have 3 African-American Catholic religious groups. We have a number of small Latina groups in San Antonio that we test in Spanish. And we have about 15 places across the country that we've prearranged that when someone dies, they'll remove the brain, follow our protocol, and ship it to us in Chicago. And so these people are tested every year where they live. I started a second study in 1997. It's called the Rush Memory and Aging Project. It now has over 2,400 persons, without dementia, that come from the greater Chicago area. Again, everyone agrees to annual clinical evaluation and blood draw. In this study, everyone agrees as a condition of entry to donate not only brain, but spinal cord, muscle, nerve, and more recently, bone and fat at the time of death. Many have also agreed to repeated biomedical device data collection and MRI. And again, we have over 400 cases of incident dementia, over 625 cases of incident MCI, and we now have more than 1,100 autopsies. So Rush University Medical Center is on the near west side of Chicago. We work with primarily continuous care retirement facilities across the Chicago area, Cook and the Collier counties. And then we also work with social service agencies and church groups, and we enroll and test a lot of people as individual home visits across the city to ensure greater ethnic and racial diversity and socioeconomic diversity. Because we basically drive to all these places, we don't have to get on an airplane. We can bring more stuff out, and that's why we can bring out all these biomedical devices and all kinds of other things that we can put on them and then retrieve from them. The 2 studies are harmonized at the item level, so the recruitment, the testing, the autopsies, everything is done by the same team, and so we can merge the data at the item level. Because the Rush Memory and Aging Project is all local, there's a lot of things that we do in that study that we can't do with the Catholic nuns, priests, and brothers. Some of them, they don't want it. Some of it, they don't have time. And some of it, we simply can't get the stuff to them in an efficient way. But here's the designs of the study for both. We enroll at baseline without dementia. We document risk factors. And we test them every year for incident disease, for change in function. And this part of the study has all of the features of any prospective analytic cohort study of risk factors for common diseases. We layer on top of that the autopsy. So everyone must agree to organ donation as a condition of entry. And so over time, people also die. And so within a single study, we can look at risk factors for the occurrence of disease, risk factors for change in function. We can look at the biology, underlying disease proximate to death, underlying function proximate to death. We can look at the biology in relation to the trajectories of change in function over multiple years prior to death. And even though you get the brain at the end of the study, if you're looking at loss of cognition is the output of the brain. And so with a little mental gymnastics, you can think of things in the brain as mediating the exposure variables and the outcome variables. So this is what aging looks like. This is here with age as the metric. And what we're interested in is understanding person-specific differences in slopes. Actually, person-specific differences in the intercepts, but also, but especially person-specific differences in slopes. This is from a linear mixed model. It makes those nice straight lines. But why are these people declining so much more rapidly than these people, so much more rapidly than those people, and these people not declining at all? So what accounts for those person-specific differences? And you can see, we can see this across a wide range of age, this declining. Another thing to realize is these people in blue, this is a random sample of participants, this is the raw data, who developed Alzheimer's dementia. And the green are people that did not develop Alzheimer's dementia. This is a random change point model. We simply asked the computer, can you find an optimal change point? And here we see about 5 years into the study, the rate of cognitive decline among people that develop incident Alzheimer's dementia increases markedly. But you notice they were declining pretty rapidly before that. And the people that didn't develop Alzheimer's dementia are also declining. I could do this for incident MCI. The curves are not as steep, but you see the same thing. And so we label people as having a disease or not, like Alzheimer's dementia. But in fact, this is a continuum of decline. And where we label people is simply a matter of something that the field comes together on and agrees. And there's a lot of good reasons to label people. We label people so we can count them. We label people so we can share information with patients, with families, with funders. We label people so we can count how many are going to be in the future. But to understand the underlying biology of these diseases, it is better to ignore the label and just look at the trajectories, because that's what we want to understand. And so at first, a lot of the stuff that we're going to do is looking at predictors of decline. Why are people declining? And I'm not going to go into all these, but this is just a sample of the risk factors that we have published that are related to cognitive decline. A large list of genomic risk factors. Some of these we've published alone. Some of these we've published as part of consortia. And then a wide range of experiential exposures, psychological exposures, medical exposures, and then we're measuring old people, so we measure a lot of other stuff, a lot of health and financial decision-making, susceptibility to scams, purpose in life, and then a lot of physical function, and gait, and frailty, etc. And what we see is that loss of cognition is a complex function of multiple genomic, environmental, experiential, psychological, and medical risk factors. So now I'm going to flip to the other side of this study, where here 0 is the time of death. This is a random sample of participants looking at their slopes over multiple years prior to death. Here we can clean it up with a mixed effects model. And here this black line is, this solid black line is the average decline. And here we see people declining faster and some people declining slower. And again, the question is, what accounts for these person-specific differences in slopes of decline? And in this case, what can we measure in the brain that accounts for those person-specific differences in slopes? And so here's the kinds of pathologies that we can measure. This isn't all of them. This is a classic silver stain that would have been used by Dr. Alzheimer. It's a Bilshowski stain. You see these classic neuritic plaques, diffuse plaques, neurofibrillary tangles. We can look at the distribution and amount of those across the brain and come up with a pathologic diagnosis of Alzheimer's disease, where if you're above that, you have pathologic AD. Below that, doesn't mean you don't have any pathology of the disease, but it means that you don't meet the threshold. We also can count these in a way and get a burden of AD pathology. This is a sticky substance. It's not molecularly specific. For that, you need to do immunostaining. And so here is immunostaining for amyloid beta. We can look at the percent area of the tissue occupied by amyloid beta. This is antibodies to paired helical filament tau, so we can look at the density of tangles. This is A beta in the blood vessels, which is amyloid angiopathy. This is TDP43, which is a mislocated protein. It's phosphorylated, but it's also mislocated. It's supposed to be in the nucleus, and then we see it in the cytoplasm. Cortical Lewy bodies. So Lewy bodies are the classic pathologies that you see in Parkinson's disease and the substantia nigra. Here we can see them up in the neocortex. This is hippocampal sclerosis. This is scarring of the hippocampus, usually with loss of neurons. And then a variety of vascular markers. Atherosclerosis. This is the basilar artery. Middle cerebrals, the vertebrals, this yellow crunchy stuff is of atherosclerosis. Arteriolar sclerosis is a thickening of the penetrating arteries. And then infarcts. So these can be macroscopic infarcts that you can see with the naked eye, or they're microscopic, meaning you can only see them under a microscope. And it's basically a hole in the brain that's filled with cerebrospinal fluid. So a piece of the brain dies, it gets cleaned up, and then it's replaced with spinal fluid. And if we ask the question, how much of decline do all of these pathologies account for? This first line here is the so-called group with no pathology. It's the mythical no pathology. Everyone has some pathology. So it's people that just don't meet the threshold for pathologic AD or any of the other pathologies. This is pathologic AD. This is the rest of the neurodegenerative diseases. And this is where we add the cerebrovascular diseases. And all told, we can account for about 43% of the variability. It says variability of decline. That's not true. It's the variability of change. Remember, some of those people are showing some practice and improvement. And so we have this residual cognitive change of over half. And then it gets a little bit more complicated, because if we look at the various combinations of pathologies in the brain, we see that the most common is pathologic AD alone, but it's in less than 10%. And then there's mythical no pathology, meaning they don't have any of the other pathologies, but they don't meet the threshold for AD. And then you start getting into combinations, and very soon you're getting into small numbers of people, and then you have this tail of almost 100 people where there's one person that has that particular unique combination of pathologies. Right? So this is almost 250 people out of, in this paper, was about 1,100 brains, actually fewer than 1,100 brains. All right, so when you think about all these different pathologies, when you think about what it is that we're trying to treat, what we're trying to prevent, okay, this is what's happening under the hood. And it's a bit more complicated because, remember, we only account for about half of the cognitive change. And so if we ask the question, how much of the variability of decline does any individual pathology make? So even if it makes 100% contribution, it's only 100% of the half. All right, so for all these pathologies, it really depends what you're in the head, who your neighbors are. If you're in there alone, you can count for all the decline that can be accounted for. If you're in there with a bunch of friends, okay, then you're going to count for much less. So all of these range from 20 to 100%. Since it's only half, it's really 10 to 50%. It looks a little bit better when we think about how much can we explain of pathologic Alzheimer's, of clinical Alzheimer's dementia. These pathologies are capturing the decline. They're not capturing the little bit of practice and improvement. And so it turns out this is demographics, this is pathologic AD, this is the other 7 pathologies, this is a dummy variable for unaccounted for cases, and in total we can account for about 2/3 of cases of Alzheimer's dementia with all those different pathologies. Still about 1/3 that's unaccounted for, and AD is about 1/3. So AD is still the elephant in the room. And so loss of cognition with age is a complex function of multiple genomic, environmental, experiential, psychological, medical risk factors. It's a complex function of multiple brain pathologies. Together, they explain about half of cognitive change. There's hundreds of combinations of pathologies. Each one can explain 20 to 100% of the explainable half of change. And together, they account for about 2/3 of dementia, Alzheimer's dementia. Okay, now, your brain does not want to be demented. All physiologic systems have ways of protecting themselves, all right? In some cases, it's pure redundancy. You have 2 kidneys, you have 2 lungs. In some cases, you can grow the tissue back. I can take out 90% of your liver, and you can grow your liver back. Your brain is in the ultimate high rent district. It's constrained by the skull. The skull is constrained historically by the width of the mother's pelvis. All right, so there's only so big it can get. So what is in here, and how are we going to figure out what this residual is? Okay, so residual cognitive decline, I'm going to use called resilience residual cognitive decline. So what is this? We regress out the effects of the brain pathologies, and we're still left with a bunch of person-specific slopes. So now there's no pathology here, but this is still the residual slope. Here's the average person, and this person has average resilience. Okay? Here's people declining slower. They have more resilience. And here's people declining faster. They have less resilience. We're interested in both of these. We're interested in what helps maintain your brain function, your cognition. We're also interested in what else is going on that might drive cognitive loss, all right? Something other than the pathologies. And so we can leverage deep omics to look at this. And so we have genomic data. We have a variety of levels of epigenomic data, including microRNAs. We have the transcriptome, the proteome, the metabolome, and some of these we're just generating constantly more and more data sets. I'll let you look at it this linear way, which is we start with our risk factors. What is it we're trying to prevent or understand? Is the syndromic phenotypes like Alzheimer's dementia, mild cognitive impairment? And what's the path where we're going to get there? Well, there's the epigenome, epitranscriptome. Most of this is brain, transcriptomics, proteomics, metabolomics. Then we get into quantitative neurobiology, structural and functional MRI, a bunch of blood biomarkers. Our quantitative traits, here's our 21 cognitive performance tests, clinical diagnoses. Remember, we're also getting spinal cord and muscle, so we're doing proteomics and metabolomics and transcriptomics also in the spinal cord and muscle. We have motor function, a variety of other biomedical devices and other types of phenotypes that we can examine. And this is all there in the database, all available to anybody who wants it. You need to sign a data use agreement. So this is a Chicago plot. If you've not seen a Chicago plot and you're wondering, David, you're from Chicago, did you make this up? The answer is yes. I take full credit for it. Okay. I love the Chicago plot. Okay, why? Well, first of all, Chicago is a beautiful city. Okay, you want to pull up Manhattan skyline? I challenge you to find me something that's pretty. But the other thing is the standard Manhattan plot gives you the p-value. It doesn't tell you the direction of the effect, and it drives me absolutely batty. So here is a proteome-wide association study for resilience, and we find all these guys up here that are associated with more resilience, and this little fellow over here that's associated with less resilience, all right? They're both interesting, except you would just move these things in opposite directions to try and improve brain health. And so loss of cognition with age is a complex function of multiple brain pathologies adding to interacting with multiple resilience markers. So that gets us to complexity, embracing complexity, all right? All of these risk factors, all of these pathologies, all these resilience markers, okay? And if you want to put this in a mathematical formula, and this is not with the risk factors, this is just what you measure in the brain. So cognitive function Cognition is a function of is the observed cognitive score, and it's a function of the observed pathology, observed resilience, the interactions between pathologies, the interactions between resiliences, the interactions between pathologies and resiliences. And I went ahead and I put a dummy variable in for all of the pathologies and the resiliences that we have yet to discover and therefore can't be in this model. All right, so in truth, it would just be in the error term, but I like to put it there as a reminder, all right, that this model will forever be incomplete because we will always be discovering new things in the future. So how are we going to go from all of that to precision medicine for a disease of the brain? Just so you know, this is my son makes these pictures for me. So the first part is, can we predict brain omics with data from the same living human? So we have all of this omics in the brain. It's all really cool stuff, but all those people are dead. Okay, I cannot help them. Okay, I'm a neurologist. Okay, the question is, how are we going to get from all that beautiful information, all right, and try and figure out what does it mean in living people? So here we have several layers of omics from the brain, okay? And we're going to put this into a model. It's called a contrastive PCA. And basically, what a contrastive PCA does is you define a healthy state, a desirable state, in this case, no cognitive impairment, and you define a undesirable state, in this case, Alzheimer's dementia, okay? And it orients all the omic data, all right, into what's called a pseudotime. It's pseudotime because it's not really time, because it's all cross-sectional data, but it's pseudotime in terms of the molecular distance from your desired state, no cognitive impairment, to your undesired state. And so you can put all of this omic data in there, and you can see what your molecular space looks like for your NCI and for your AD, for your Alzheimer's dementia, and then you can see how far somebody is along that space. And that's what the pseudotime is. And it just goes from 0 to 1. So everybody has a pseudotime 0 to 1. You can then put this into multidimensional omic space, and you can ask the question, how many different pathways from 0 to 1 are there? And it turns out that 3 is the most parsimonious. And this is what these pseudotimes contribute to. So it turns out all of the levels of omics are contributing to this pseudotime, and then these subtypes as well. All of these are contributing. So all of these omics are important at some level. Okay, now we're beginning to make the transition to the living person. So these levels of omics are all from the blood: cell-free DNA, monocyte RNA-seq, proteomics, metabolomics, and p-tau 217, 180, and 1. And now we're going to use them to predict our 3 different AD trajectories. Okay, so that's 15 different associations. We can't put these in the common space yet because the overlap isn't sufficient, because they were all chosen for different study reasons. So the first thing you notice is p-tau is basically chance. Now, I'm not saying p-tau in the blood isn't important. I'm not saying it doesn't predict tau in the brain. I'm just saying it doesn't predict these molecular trajectories. Cell-free DNA does a little bit better. Monocyte RNA-seq does a little bit better, but the best right now is proteomics and metabolomics, where we can get AUCs of up to about 0.8. So we're just beginning to get to the point where we can actually define molecular trajectories in the brain, okay? And then we can use blood omics to predict those molecular trajectories. Omics I can get from each one of you while you're still alive. And I think once we get more omics and we get more overlap, we're also doing some math to improve some of these models. It's not inconceivable that we can get up to 0.85 or 0.9 even. Okay, the second thing that we want to do, once we can define these trajectories in living people, is we want to be able to interrogate the little brains from these people. And so it turns out we can probably do this with iPSC, induced pluripotent stem cells. This is a polygenic risk for Alzheimer's dementia, cognitive decline, and the various pathologies. And so there's a very strong polygenic risk for AD clinically and pathologically. And so we can take advantage of that by making iPSC lines. So here what we're doing is we're taking the cryopreserved PBMCs, the cryopreserved white cells. So we took white cells while they were alive, we froze them down in a way that we could bring them back to life. And then we take, in this case, we started with 53 people. We actually started with more. We ended with 53 people, where we were able to make 53 different iPSC lines. 53 lines from one each from 53 people, all of whom have come to autopsy. So we have all the clinical data, we have all the pathology data, we have all the omic data from the blood, we have omic data from the brain, okay? And now we have 53 cell lines that we can induce into neurons. And so what do those neurons do? Well, it turns out that they make A beta and tau. They make a variety of different species of A beta and tau. All right, so these are newborn neurons. When I say newborn, I don't mean 9-month newborn. I mean like 2-month in utero newborn neurons. And there they are, pumping out A beta and tau species. They're correlated with one another. They're correlated with the neuritic plaques and the neurofibrillary tangles from the brains of the same 53 people. Drum roll. They're correlated with global cognition, slope of global cognitive decline. They're correlated with global cognition at the last visit. They're even correlated with the MMSE score. So here we have these little infant newborn neurons pumping out A beta and tau. All right, I didn't mention this before. They're related to the polygenic risk of AD from the same 53 people. They're related to the pathologic and the clinical data from the same people. So now we have a model, all right, of our autopsy participants in a dish. Oh. So per specific differences in A beta secretion from PBMCs. So I just said this, I'm not going to repeat it. So you can imagine future studies where you do compound screens, all right, and you do compound screens and look for something that alters A beta. All right, you find out which ones are enriched in their genomic subtypes or maybe other omics in the blood or other data, okay? And then you have to go grab another set of lines that are enriched with those things and rerun your experiment. And this is your path to a personalized, not personalized, precision medicine that actually follows a path that's similar to what's been done in cancer, except with cancer, I can do it with the actual tumor, all right? And here, I'm gonna need to do it probably with iPSC lines. So, loss of cognition with age, complex function, said it before. So I asked the question, is it wise or practical or affordable to develop biomarkers and cocktails that individually target each pathology? When you think about resilience markers, they exert their effects agnostic to brain pathologies. There's simply no evolutionary pressure to develop separate resilience systems for separate age-related brain pathologies. So can resilience serve as a therapeutic target? So here, this is a study we did now a few years ago. These are co-expression modules of RNA-seq. They're put in a Bayesian framework. You can get these putative arrows, okay? And here we see this module 109. It's got a small edge to A beta and tau in cognitive decline, and it's got a thick edge to cognitive decline. The thickness of this edge is related to the strength of the association. The length of the line is meaningless. It just allows you to see what's connected to what. But basically, this is a module primarily of resilience because it goes directly to cognitive decline. I'm not showing you all the other pathologies. They're also in this model. And so here we're looking inside module 109. It's 390 genes, which means it's 390 proteins. And in this case, we're going to measure some of those proteins. Now here's the association of a number of proteins associated with cognitive decline. We're not looking for the strongest association. we're looking for something that's significant, but not necessarily the strongest. We're looking for something significant that is not related to brain pathologies. And so here's two, AK4. And you can see it's not related to any brain pathologies. ITPK1, it's got this modest association with tau tangles and nothing else. And now we can put this in a model with demographics and pathologies, and we see that AK4, higher AK4 is associated with a more rapid cognitive decline, controlling for pathologies. AK4 is bad for your brain. ITPK1, good for your brain. It's associated with a slower rate of cognitive decline. Now, if we go back to our iPSCs, this is our 53 iPSCs, and now I'm just showing you the differences in pathology. So you can see a lot of these lines come from brains that have a lot of different brain pathologies, a great mix of brain pathologies. And so we have an opportunity to model resilience in a dish. And here is AK4 measured from the dish, okay? And here is the association of AK4 with residual decline. So this is AK4 from the dish associated with the clinical and the pathology data from the same humans. And so I can replicate with the AK4 from the dish what we see when I measure the AK4 in the brain. So, and we've recently generated 57 iPSC lines from African Americans, and we're now doing the neurons in the glia, and so we'll eventually be able to do ancestry in a dish. So these are the brains that we have, and I have one more little section to go through. 2159 brains. 3 of them are under age 65. The mean age is 90. 70% are women, less than 10% non-white, less than 3% Latinx, and 16 years of education. So we have a problem. What is the problem? The problem is this. We're missing a big swath of our planet. So that brought me to Brazil. So I have a study in Brazil. It's called PARDOS, Pathology, Alzheimer's, and Related Dementia Study. PARDOS in Portuguese means brown or mixed, meaning brown people or mixed ancestry. So in the state of São Paulo, in Brazil, the actual census is white, black, and mixed. We work out of a university in São Paulo called IAMSP, and we work out of 2 autopsy centers in adjacent suburbs. This is San André, and this is Guarulhos. And we've been working there since August of 2021 in San André, since August of 22 in Guarulhos, and they built an autopsy suite for us at the hospital, and it took a long time, but finally we had the approval from public health to go ahead and start doing autopsies there. So, how I learned to stop worrying and love Brazil. I don't know if you recognize what movie that's from, but my second time in Brazil, I got held up with a gun pressed against my head and somebody who said something in Portuguese, which I assumed meant give me all your money, which I did. So, since August of 2021, we have collected 3,373 brains. Over a third are age 18 to 64. The mean age of the old people are 78. The mean age of the younger ones are 53. Over half are men. 43% are non-white. They're all Latinx. There's actually a number of Japanese and native Brazilians as well, and they have an average of 6 years of education. So we're getting in Brazil basically everything that I can't get in the United States. And we're already funded for whole genome sequencing and its derivatives, ApoE, Tom40, and we have some money for genome-wide DNA methylation and RNA-seq. So that's really nice, David, but you only have informant interviews. True, but we have one other thing that I didn't mention yet, and that is I don't know how this comes through okay. That's the palette of Namur, okay, which is the first depiction of a decapitation. So you realize that your brain talks to your body. Here's another depiction of a decapitation that much more familiar to some of you. And then you might think that the French perfected this with the guillotine, but in fact, they stole it from the British. So we've long known that the body and the brain talk to each other, and in Brazil, turns out we get the body. No, we don't get the whole, we could get the whole body. I have no place to store 3,375 of these things. We're getting 6 to 8 a day. But we can take pieces. So the first thing that we're approaching with these bodies is how can we interrogate them for the three most common sources of pollution worldwide, which is air pollution, water pollution, and food chain pollution. And so we're collecting teeth and bone. So turns out your teeth is your early life deposit of metals. Metals are deposited in your tooth, okay? And as you drill through the tooth, you're actually drilling back in time. So the metals on the outside are from the younger tooth, and the metals on the inside are from when the person was younger or the older tooth. Okay? Of course, that only gets your early life metals. Okay, your bone is your major metal depot throughout your life. Anyone recognize this? This is lung. You heard of black lung disease? Okay, that's carbon in the lung. It's a nice pink lung. It's a nice, not nice, it's kind of ugly actually. Here's a beautiful pink bronchus. And here's a bronchus with a lot of carbon. So we can get a carbon footprint. We can get a footprint for particulate matter, PM 2.5, which is the most common stuff floating around in the sky that you breathe in. And then this is abdominal and pericardial fat, which are your major depots of persistent organic pollution, along with the liver and the brain. And so we have a lot of data. We're collecting more data, and now we're collecting more biospecimens that I have places to store. We like to give it away. So that's the website. You can go to our website. I'm not going to give you a tutorial on how to work it. It's supposed to be self-explanatory. If it's not, there's a little tool there that you can actually put in a question to the people who maintain the website and say, hey, I need more information on whatever. And it'll go directly to them. It'll be tied to the page that you're looking at. And so with that, I thank you very much. And if there's any questions, I'm happy to take them. I do have a little bit of time before my taxi arrives.
Yesterday we saw vitamin D, and there was a short blip of around nutrition. I didn't see that as one of the risks.
It's in there. It was in there as a diet, the MIND diet, the DASH diet, the Mediterranean diet. Yeah, so we do the food frequency questionnaire every year. We have a whole number of grants around diet.
Fantastic. No, thank you. I just missed
Okay,
it.
yeah, and if you go on the hub, you can get the diet data.
Fantastic presentation, David. And you're such a visionary doing this, right? I knew about the Brazil study, but it's wonderful to see how it develops. I had a question on another topic, namely how well omics predicted compared to tau. And a part of it, I know that you guys have very in-depth characterization of metabolomics, for instance. And is it also a numbers game? How much data do you need to predict well with metabolomics? Because most of us, sometimes you're working with NMR data, which are basically
How much metabolomics data?
Yeah, how much did you input there to predict well? Is there?
Yeah, that's
because you are in depth, right?
Yeah, there's a variety of different metabolomics platforms. Right now, this is just the targeted platform. So this is the Biosocrates from Metabolon. So we are generating lipidomics, I think it was in there. We have some glycoproteomics. I mean, so and then there's untargeted metabolomics, which gives you a whole bunch of stuff that nobody knows what the heck it is. But you can put it in and then figure out, if they're important, what they are.
So if tau isn't the best readout, but metabolomics is then the metabolic mess that happens after the diagnosis, the real measurement.
That is the reason at the end of the day we need to do experiments in some system, because we fundamentally cannot, disentangle it when we get out that far. Which one is driving what? I mean, there's certain things we can do with the genomic prior. All right, but even there, you'll run into recursive processes where the genomics will eventually drive a pathology, which of course will drive something else downstream. All right, and that's why we're making these iPSC lines. All right, so we can then interrogate these things, because without that, we'll never know. We'll be chasing our tail.
One more.
Yes, sir.
One more here.
Go ahead.
So it's great work on the on figuring out the exposures. So I guess there's been a lot of interest in microplastics. I'm wondering whether you've looked into that and which tissue you want to-
Microplastics.
Yeah.
Yes. So there was just a paper that came out in New England Journal I think a couple weeks ago, where a group found microplastics in the arteries that they were looking at in the heart. And so we're actually now, we actually have approval to take the heart and the vessels. We haven't been taking it, but now we have a good reason to do so. I just got to find some place to put it. Maybe not the whole heart, just a little piece of it.
And if I can have a second one, have you started looking at the differences of exposure between the Brazilian cohort and the US cohort?
Are we going to look at the differences in the exposure between the Brazilians and the US cohort? I'm not sure that we will actually end up doing that directly head on. I have never done a head-to-head comparison of the nuns and priests and the lay people, because there's such, I have looked to make sure that the associations are the same, but that's different than looking, to see whether the exposures are different and stuff like that. The Brazilians are so different, but all of these pollutions are the same pollutions we see here, because the way the world is connected, it doesn't matter who dumps the stuff in the sky, it ends up, we're all breathing it in. And the same thing with most of the water. Some waters are local.
One more question, sorry, here. Okay, very
One more. Where are we?
Over here.
Okay. Hi.
Thank you for the very interesting talk. Could you very briefly talk about your engagement with the Brazilian communities?
The engagement with the Brazilian communities?
For collecting the samples and all of that.
Okay.
Thank you.
So right now we enroll people dead. So the people we're engaging are the people that are either going to the autopsy center or going to the hospital to retrieve the body of their loved one who died, within the last 8, 10, 12, 20 hours. I am planning to pilot a map-like study in Brazil. I was just there a month ago. I'm going back in June. So I'm taking from one of my grants in the US, and we're working with NIA to move some money down there, because I do think we can engage through the hospital. So the hospital is the hospital system for all the civil servants and their family members in the state of São Paulo. And so I primary care as well as a tertiary care. And so we're planning to engage through a few different clinics, like ophthalmology clinic, for example, dermatology clinic, to enroll people for annual evaluation and organ donation. The city of São Paulo recently, because recently passed a law that if you die and you're buried in the city of São Paulo, you must use one of four funeral agencies. And so we've met with 3 of those who've agreed to let us do autopsies in their space. If somebody died. So we're putting the pieces together, and based on our experience with so far 3,500 autopsies in 2.5 years. These people are remarkable, but we'll see how it goes. Until I've done it, I haven't done it. All right, thank you.
Good morning, everybody, and thank you so much for inviting me. I'm a little bit wondering why you are inviting me, because you have shown so many interesting data and have such an impressive infrastructure, so that I'm in doubt that we Scandinavians can significantly contribute. But I take the chance and will maybe distinguish myself a little bit from the former speakers, because I not any longer consider myself being a researcher. Maybe I'm an innovator or an implementator, because we see a huge discrepancy still between what is possible and what do we know in research and what is reaching really the populations worldwide and especially in global health. Quickly, I have to disclose that I'm also a shareholder in a company, a spin-off company, which is called BrainSynth, and I'm used by Roche and Eli Lilly as speaker. I'm heading the European initiative called AI Mind, and we are 18 partners from 8 countries at the moment. One of the partners will leave us due to impartiality reasons, because it is one of the big notifying bodies called DNV. And since Roche entered Roche Pharma and Roche Diagnostics, the partnership, they prefer to stay outside. We have another big, large European funding gotten through the eBrain Health consortium, which I will later attribute as well. So both fundings will help to introduce not only a federated infrastructure for sensitive personal data in Europe, but as well to develop and adapt our developed algorithm. What is the story? The story seems maybe for many of you either known or maybe boring, and that is that it is a fact that we in Europe, in a high civilized society, still need up to 8 years to diagnose people at risk who suffer from MCI. As we know, not all of the MCI candidates are at risk, and we also know, as Ashton noted or mentioned yesterday, there will be still years to come before the blood biomarker are in a reliable clinical sense established, and as well they will not identify specifically or discriminate necessarily to a degree of certainty alone the truth. Therefore, we wanted to develop a globally achievable, affordable method for screening reasons, and not only for screening, also able then by specific biomarkers in an add-on procedure of the algorithm to say a little bit more stratified about whom we have in front of us at a stage when the diagnosis is not given, and at a stage where the person subjectively recognizes cognitive changes. Therefore, we went back to an old technology, which is very much achievable, and everybody, or almost in Africa or in Asia, accessible, and that would be an EEG. And we then went back to old mathematics 20 years ago, 25 years ago, developed with the math for functional brain network analysis. But as you know better than me, it never made to any clinical relevance due to too high load of expert-driven knowledge in these analyses, neither in fMRIs or EEG or whatever you would take, have made it to clinical significance. So meaning the EEG has to be analyzed in a completely fully automated manner, and it should not be touched by human, it should not be cleaned by human, the noise reduction and so on. Everything will be done by a machine. When we have then these information about the functional brain networks, then, or at least the discrimination between pathological or non-pathological, then we feed the algorithm with additional information, and in dependency what you want to know from the disturbance of the functional networks, you can then add on specific biomarkers or cognitive results, whatever you wish, as long as it is digitalized. Because of the resistance in the medical establishment towards deep learning, we originally, when we wrote the application, favored that we would start machine learning in parallel versus deep learning approach. After a while, during the last 3 years, quite a lot has happened worldwide. So we favor internally, for sure, the deep learning models. And then the predictor in itself, which is an add-on or fed-on procedure, is then for sure more classic machine learning driven. If we are estimating your risk in the group of subjective to mild cognitive impairment, then we are still far away from personalized medicine. That is a reason why we think we are now in the position that we are able as well in these selected cases on the platform to add on the virtual brain simulator, and that we could for sure be now in the stage that personalized individual prediction with the perspective of hypothesis-driven analysis is possible. It is possible, and you have to be a little bit patient because these results we will launch at CTAD this year, our results. But it is still a fact that the clinical equipment, at least in most of the European countries, is not good enough to make it possible. And that is, in fact, a challenge, that the infrastructure, the server capacities, especially in the combination between AI and simulation, is so heavily energy demanding that most hospitals will not be in the situation to be able to do so. But when we wrote the application again, the vision was also that maybe it is not meaningful any longer that each hospital or each city would have such capacity for itself. Maybe it is possible by federated infrastructure, that some of us and some cities would have the capacity to analyze some of the algorithms available. So what we then also planned was that we build and start an infrastructure which would then give the accessibility internationally to send your data, and then you will receive a requirement list which kind of data quality management and governments you have to respect to be eligible to approach the server and get then the analysis done and the result back to you. Simon mentioned that all this is, of course, and many of the questions from the former speakers were referring to it, in the little example of Alzheimer's disease, it is of course already clear that we are talking about a syndrome and not a disease, meaning that you will need unbelievable many participants if you wanted to reach the so-called ground truth in one or another patient. We think we are also able, and AirMind is working on it, to synthesize most of the realities we could then build in a virtual room. Also, this is for sure soon reality, and it would help especially within rare diseases and everywhere where we suffer from compliance in clinical trials. What is the biggest challenge, at least from my point of perspective? And there is a lack of understanding between IT, AI, and medical world. And this lack of understanding, which is maybe not present in this room, but mainly in most of our research settings, is so significant that we need to change our educational systems as soon as possible, but reaching from school and leading to universities, as not even IT people are really communicating this within the same language understanding than AI. And it demands, the modern data analytics will demand that the three main groups are really talking to each other, and not only talking, understanding each other. And especially for, I'm pretty scared at the moment about the explosion of AI algorithm development, as it is mainly bullshit. Because the bullshit is that everybody can build an algorithm about something. That's not a problem if you are a little bit gifted as a mathematician. It's easy. It's not rocket science. But you have to understand which data you are handling and how you required the data. So one aspect we worked in AirMind with was that the AI people had to collect the data. And that was a tremendous experience. They had never seen patients. They have never signed informed consent and so on. They did not know what this is, and they are usually not interested where the data are coming from. They are interested in data. but their critical ability to evaluate data is depending on that they understand where the data are coming from. And this was a wonderful experience, and I can only encourage you, start and exchange the roles. And the medical doctors should go back to the math books and should learn a little bit more mathematics again. This is urgently needed because otherwise we are really developing for nothing. As I mentioned, we will not come in neurology to personalized medicine if, and this is another challenge, if the AI prediction world is not understanding and again working together closely with the simulators. Simulation is more for us in medical science more understandable because it is more hypothesis driven and because it acknowledges our physiological understanding which we have had for hundreds of years. But we need this combination to really make an effort for our patients. And therefore we are here. We are not here to make exclusive science. We are here to help. And that is in medicine a very important issue. And if we want to reach and be better with an algorithm than a doctor, then we have to acknowledge that the doctor, for thousands of years of medical history, has understood by a view very much, very quickly. And the algorithm will only be a little part and can only support the richness of understanding, which for history, throughout the history, has contributed to a real world-based understanding of a complex issue. As I mentioned, as long as we are not working with our governments on infrastructure solutions, we will fail. And as long as we as well not agree on, and as a community agree on how we standardize our data. That is also an issue which became very prominent in the AirMind and in the e-brain health action, that is the real lag. Why is an algorithm developed on 40 or 50 or 100 patients? That is not sufficient. You have to develop it of many 10,000 of people. And then you have to standardize everything. And very important, until today, except maybe 1, 2 algorithms for radiology, none of the algorithms has really shown that it is really cost efficient. And what is the real outcome for our nations, for the better good of patients. And to be able to do so, we need also criticality assessments, like in industry. And we need these criticality assessments within our understanding what is important and non-important. And we had yesterday a very nice conversation about the curation of data. This is, for example, often not in the focus of researchers. And I dare, most of your data banks are not sufficient for industrial use because you are not curating exactly enough. You are not describing exactly enough. And whom of you have really developed an algorithm and explained to the notifying bodies why you made in between, in deep learning, which kind of decision. When did you stop the machine and which deep layer you favor it and another not? You have to explain us all this if we later, as doctors, should believe you, should understand your logic of thinking. And it is until now in science a prerequisite that others are unable to understand what you have done. And you can explain deep learning. It's not a black box. This word black box, I never understood. Why is it black? It is understandable, but it's not understandable in a common sense. So what did we do? In four clinical countries, also countries where we collected data, we standardized everything by QR codes. So every doctor at a hospital in Roma or in Helsinki or wherever did the same. Put his mobile phone or iPad on a QR code and was led directly to one server placed by accident in Norway. And there the registry was done. All clinical information, all standardization, all calibration of machines, everything was standardized. This is important to be really efficient and to make it able for control mechanisms. And it makes you independent, that not everywhere you have, again, to hold the same accuracies. And then we were so fortunate to achieve another large-scale funding. As I mentioned, that we then merged in a federated infrastructure our sensitive server within a federated infrastructure with other countries. And that because we knew, of course, that when and if we are developing our algorithms, then we know, of course, they will never be good enough in the next nation. We need data, more data, and deep learning needs a lot of data, and it's very hungry. So then if the UK wants to use AI-mined algorithms, fine. Then we can make it possible that you add on and that we are adapting the algorithm and make it more reliable for your society. A very important step forward was then the partnership with Roche Pharma and Roche Diagnostics, as we then understood that we should be able for the adaptation and preparedness for the future of our algorithm, that it is not a static product, but that it will be available to predict as well with the forthgoing research in that biomarker. I said this before, and I think a game changer was reached in fall 22 when the FDA for the first time allowed a clinical trial with synthetic data. And I think that will be also the discussion about the biological value or the biological representativeness of synthetic data is, of course, very important to be solved. And as you know, maybe better than me, quite a lot of projects are around the synthesizing of data at the moment. What we want to achieve for sure is that we, within the next 2 years, or maybe already within the next year, are able to document that our algorithms fulfill criteria for technical readiness level 7, and that we would then, with the manufacturer, be able to go to the EMA and FDA and could let register our algorithm as a medical device. But what I said as a side product and what was really important is the standardization, the agreement on data governance, data management, and curation. The curation, there does not exist a language in curation for algorithm development. That is also leaking. We need a language how we want to describe algorithm development. What is it doing in medicine? As I mentioned, pro and cons, and why I choose one way in favor of another. This is also very important, and it is urgently important if we really want to make it into the medical device world. The last, but maybe one of the most important steps, which is not even touched when we are talking about standardization and curation, is the communication towards the patient. That is in the European Commission, worldwide not solved, but also not in the European Commission. And I guess we will harbor into a situation that we need, like in pharmacology, a documentation which is sent to the patient, which the patient can read, and where it is also exemplified uncertainties, which are mainly under-communicated. Uncertainty is, of course, an internal mathematical problem, and it's not only false negative, false positive, it's much more than that. And it is also not stressed when using algorithm responsibility and claim consequences. This is also urgently needed, that we are sitting together and with our legal communities and agree on who is responsible. I don't think that the medical doctor in the future will be able to be claimable if he or she has used an algorithm. It could be like in the building, construction industry, that maybe also the engineer is responsible and has to cover the consequences. Then it needs towards the patient also safety and security measures. And as many legendary institutions in the US are traveling around and asking for data, I'm not sure that this is sufficient enough. The patient owns its medical files. So meaning the ownership is the citizen and not a researcher who is using the data. So that needs also to be clarified, and how this citizen is getting paid back for industrial developments. That is also not at the moment clear. It is a capitalistic harakiri at the moment, and the industry is earning a lot, but there must be a payback solution. And the national health care systems are underfinanced everywhere, so they need also, of course, modern income solutions, how that is reaching back in a good manner in at least in our democratic world. And all this will then lead to a trustworthy use of AI, which I guess everyone wishes. And very quickly, what we also developed and got a lot of attention is that we have developed predictive health economic modelings, so that we are able within each country to calculate what really the introduction of AI Mind would have economically mean for each certain country with its own financing background. And that is us at the moment in AI Mind, and thank you so much for your attention.
To international superstars giving very considered, thoughtful, intelligent presentations. And I'm going to try and do something quite different. The presentation I'm going to give is probably quite misguided. It should be labeled The Confessions of an AI User, I think. And it's quite galling that many of the funders and partners that we have in doing this research are here today. But what we need to do when we think about AI is think about AI as a range of different things. It's not one thing, of course. Most of the elegant work that we've seen so far is machine learning, and most machine learning is logistic regression, or maybe a deep neural net at most. I'm going to talk about those kind of models, but I'm also going to talk about strong AI, general AI. And I think that is the biggest challenge that we need to tackle. And I think we need to talk about some of our concerns and be open about the way in which the field is developing and the way in which we're not necessarily the drivers of that field. So let's have a conversation and let's see how it goes. All of this, of course, on some level is about innovation. The desire to do things differently, the desire to do things more efficiently, more quickly, ultimately, of course, because we want better treatments, we want better interventions, we want to help people. And one date stands out to me, 1976. And the reason for that is I often heard people say, we are years behind cancer research. And I wondered, in terms of scientific productivity, where we actually are in comparison with cancer research. But back in 1976, Apple were going great guns. This is what the Apple I looked like. It's pretty clunky, right? Who would have thought Apple would develop into a $1 trillion company? Quite incredible. Bill Gates was struggling to make money with Microsoft. He was making a profit of like maybe $20,000 at this point. It was very small stuff, selling computers out of his garage and providing support. And you can see the logo is very much of its time. So 1976 is an interesting period. And around the same time, we had the development of the kinds of cognitive tests that are still being used today. Things like the mini mental state examination, paper and pencil-based tests that the clinician would sit down with someone who's maybe concerned about their memory or other problems they might be having. And on the fly, the clinician would score the responses to the questions asked. So things like, repeat after me, lemon, key, ball. And clinicians make mistakes when they're scoring. You know, they're distracted by patients and so on. And I think you'll agree, these are limited tests. And it's surprising in some sense that we're still this is the cutting edge technology. Perhaps not, but they're still used. And other tests like ADAS-Cog are used in trials and so on. And many people have argued that we should have moved on from this stuff a long time ago. So we need to innovate. Now, 1976 is the rough year at which the rate of publication on dementia-related topics corresponds to the rate of publication for cancer. And it's shocking how much bigger the literature on cancer is than dementia. It's around 15 times larger. So when we think about cancer treatments today, that's partly where we want to be headed towards, but we don't want we don't want to wait 40 years to get to that point. So we need to accelerate, and part of the hype around AI is to try and bridge that gap and to get us where we want to be with better treatments faster. And there was really no interest in the application of AI or machine learning until around 2016. It's important to realize that this is a recent phenomenon. Now, most studies of AI relating to dementia are machine learning studies. Most of the machine learning studies use some variant on regression modeling or a deep neural net. Most are diagnostic studies, most are neuroimaging studies, and most use the ADNI data. Now, that is not great. I don't know how well you know the ADNI study, but we need to do better. So we had all the hype around big data. Data is the new oil. Remember people saying stuff like that? But of course, oil just sits there. Data just sits there. It literally doesn't do anything. It's only when we put data to work that we can make a real difference. So that's really what motivates me to try and use data more intelligently. And AI, if you really buy into the hype, can do it all. It can suck in data, it can uncover hidden patterns, it can tell you things that a human or even a conventional statistical model could never tell you, and combine them powerfully, and that will drive the field forward, or perhaps. Now, one of the challenges when you do machine learning is knowing, okay, maybe what to put in the model in the first place, but you often just take a kitchen sink approach and put all available data in, shove it all in, and you hope that the AI is going to tell you what you need to know. This is a sort of data-driven approach. And one of the challenges with this is, depending on the method you select, it vastly influences what it tells you is important. So different machine learning approaches give you different answers, and some are greedier than others. So the columns here are different machine learning approaches, ranging from simple things like correlation and variance on regression modeling through to neural nets and random forests and so on. You can see the ones on the right, there's this huge block where they want all the data. They're really hungry for data. And they'll use a very large number of features to give you the best answer that particular model is able to. But it leaves us wondering, well, okay, but what are the core features? And you can do things like average things out. There's clearly some features that all the models need to know about. And you end up with these kind of compromises. And it depends on how you intend to use the model and whether there's things like a financial cost to collecting all the information and so on. So you get into this wrangling, but it's not straightforward. So this is some memory clinic data, and we've ranked the importance of all these different clinical features. And it's a mishmash of stuff that you assess in memory clinics. It's cognition, it's health conditions. It's, you've seen lots of examples of that. David gave a wonderful overview of the kinds of features that can be assessed. So we've got a few features which seem to be very important. This is a random forest model with extra trees. That doesn't matter too much in this context. Then we've got some features which seem to be quite important, and then you've got this very long tail, things which don't seem to be important. Now, this is real data. This is from the National Alzheimer's Coordinating Center, so it's lots of memory clinics across the US. one thing that's interesting is you can mix up real world data with junk data, and you can do that deliberately. And one of the, I don't know if you could see the little red bars here, but that was 4 fake variables that we did openly put into the data set to see how they would perform. Now, they're not all the way over here with the least important features in this model, and that's important to know. They're kind of, if anything, a little bit towards the left, right? Now, the distribution of those features was modeled on real data, but they're randomly distributed. So they truly are junk, plausible junk though. So we need to do things like this a little bit more. We can do things in simulation where all of the data is in some sense fake, simulated, if you're being kinder with your language. But I'm really interested in mixing real and simulated data in this kind of way. And sometimes it can provide us with a bit of a sense check in terms of what we're doing. Now, these features for this particular analysis are ranked in order of importance for, does this patient have dementia as it's clinically assessed, yes or no? But we can leave them in the same order and ask a different question. So how important are these features for the differential diagnosis of these patients? Now you see a completely different pattern, as you would expect, right? The features which tell you whether a patient has dementia or not are not important for the differential diagnosis. And in fact, the features all the way over to the right, which tell you nothing about whether the patient has dementia or not, were very important at differentiating between key dementia subtypes, like vascular dementia, Alzheimer's disease, frontotemporal dementia, and so on. So again, the data that you need very much depends on the questions that you're asking. And this is still a very human endeavor. Like at this point, we're the ones still asking the questions. So you get lost in data very quickly. This is a heat map of the similarity between 500 randomly selected memory clinic patients. And it's not very informative, is it? It's like an explosion in a tartan factory. And it's unsorted. What you need to do now using unsupervised machine learning is say, tell those patients to stand next to the person most similar to themselves. This is when it gets really interesting, because you're not dictating the structure of the data that model creates. So this is training and test data, separate samples of patients, and you can see quite an interesting pattern. I hope you agree these look pretty similar. And this pattern of data is based on all of those clinical features that we were looking at before. And if you relate these blocks of patients to the clinical diagnosis that they received, this is quite interesting in that bottom right is where the majority of the dementia cases lie, top left is where the majority of cognitively normal patients lie. And people with MCI are, as you might expect, as you'd hope, somewhere lying on the continuum between the two. So this is really interesting because we're not telling it what to look for. We're just exploring and allowing ourselves to play with the data almost. Now, we talked about complexity, but how complex is this? Now, we're always worried about sample sizes, particularly if you're originally trained in data science or statistics. It's like, where's your power calculation for that deep neural network? Well, that's an awkward one. Don't ask that. But how complex does data get? How quickly? Now, we've got a limited number of people in the world, so how complex will we ever have power to run our models? Now, binary variables are about as simple as you can get in terms of the kind of biological and clinical data that we have. It's often more complicated than that, but let's ignore that. How many binary features can we combine before the total number of combinations exceeds the number of people in the world? So it's a thought experiment. Does anyone have a guess? How many? No one wants to put their hand up for this one. Is 33? That's not that many. How many of the models that we've seen today have more than 33 features in? Now, this is only binary data. You can see where the so-called curse of dimensionality arises. The data becomes really complicated really quickly after you get into 20-something features. Now, one of the advantages of AI is that we can look at interactions within the data in quite a powerful way. So we criticize genome-wide association studies because they're looking at these genetic variants individually. We go, that's never going to be like that. The unexplained variance in the genetics is interactions. Okay, how many possible interactions are there in whole genome data? We're starting to get to the point where the number of people if we could have a 100% response rate, of course we can't, for everyone in the world, we enroll them in our studies, we start looking at genetic interactions, we can really quickly get lost, completely lost in what we're doing. How do we replicate that? How do we ensure that these studies are robust? This is really, really difficult to deal with. Now, machine learning models can be WYSI. Perhaps unfairly, I'm comparing things like the CADE and the BDSI, which are risk profiling tools, to models that we can derive using machine learning approaches. And you can see with these ROC curves, the machine learning stuff is better than these two existing risk profiling tools for short-term conversion to dementia, which is an unfair test because these tests were designed to look over 6 years or 20 years, and this is actually just a couple of years. So, but the most important thing is, yes, they do better. An unfair test, as I've said, but logistic regression is doing almost as well as things like support vector machines, random forests, extreme gradient boosting. There's often a lack of benchmarking in AI studies against much simpler and more interpretable approaches. You know, we talk about black box models. There's no deep neural networks in here, but it's the same argument. So we need to be careful that our models, the added complexity of the models is worth the trade-off in terms of interpretability. Now, I mentioned before that models are differentially greedy for information, and this is just one visualization of this. Some models need more data before the predictions stabilize. They all stabilize and they all end up with similar performance, but you you get there in a very different way. So again, benchmarking and comparing models is not just about overall accuracy, but it's also about things like these learning curves produced by the models themselves. Now, how gold is the gold standard of the data that we apply when training models? So, you know, the idea of being rubbish in, rubbish out. When we looked at how many people in the memory clinic data that we were using got better, we were amazed at the proportion of the data. So this is people who had a dementia diagnosis that was subsequently reversed to be mild cognitive impairment or even cognitively normal in some cases. We found about 8% in this particular cohort. I think it would be lower in some other contexts, of course, but nevertheless, misdiagnosis and misclassification will become baked in to the AI models if we don't take this kind of thing into account. And there are a number of different ways in which the data can mislead us. What we're hoping is if we say a patient has dementia and then we follow them up, we want them to stay as having dementia. We don't want clinicians to have a wobble and go, no, actually, they're cognitively normal. We don't want them to go back to MCI either, although arguably that's possibly less harmful. Now, what we can't be certain of is people who apparently recover from dementia, but then at a later point develop dementia. Now, maybe they really did develop dementia at a later point. this is, you get people classified as having dementia who recover and then go straight back to dementia and stay as dementia. Now, maybe the mistake is here. We don't know in the absence of any kind of platinum standard diagnosis. We're just dealing with the gold standard here. And then some patients jump all over the place and you just get really confused and you've no idea what's going on. So the point really is not about these examples of different ways in which the data can bake in misclassification. It's about the way in which the models that we build already have that misclassification baked in. Interestingly, though, once you know that a diagnosis of dementia is unstable and you're less confident in it, you can train models up to predict that. And then you're getting into the territory where some patients were diagnosed by an individual clinician, some are diagnosed by a consensus panel. Is there a systematic difference in the likelihood of misdiagnosis on that basis and so on? And we've had some success at predicting so-called reversion, as we're calling it. But there's a lot more work to be done to clean up the data. And I don't just mean the initial data wrangling. I mean, perhaps we should be focusing on the underlying biology more directly. Now, in terms of the data and the problems with the data, we all know that there's a huge problem with the distribution of dementia studies worldwide, and you've seen important efforts to diversify this. But the reality is that the data that we have is Northern Hemisphere, it's white English-speaking people, and it's very difficult to get around that. Now, there are studies in East Asia and Africa and so on. There's a real blind spot in South Asia, and with virtually nothing to serve a South Asian population. So there's so much bias baked into the training data that we have available, even when we try and do international studies. Another problem with AI studies in this field is when you try and read the papers that are published supposedly to explain what's going on, you can't understand them and you're left wondering what they actually did. So there are new standards coming out. There's a recent paper in the BMJ trying to improve on the reporting of AI studies, and that kind of initiative is certainly important. So what I've presented so far is are so-called narrow forms of AI, weak forms of AI, or machine learning, depending on what terminology you prefer. But of course, that's really missing the point. What we're doing at the moment isn't the cutting edge of AI. What we're seeing is general AI emerging, strong AI emerging, and I worry about how we're not tackling this head on. So the complexity of AI models is increasing almost unbelievably, and the amount of power, I mean literally electricity, required to run these models is going through the roof. The cost of running analyses is becoming unsustainable, and only the biggest of the biggest companies are able to set up this kind of model for themselves. So what we've ended up doing is repurposing things like large language models that are emerging. And you can produce your own bespoke version of large language models like ChatGPT or Llama 2 if you're using an open source version. But just to be aware that you talk about black box models, people used to worry about deep neural networks being black boxes. We knew what was going in to the box, and we knew what was coming out. We don't know what's gone into the boxes. We just know that the box is huge and is based on the internet largely. You can draw your own conclusions. So not only have we got worries about the black box, but we've got the worry that we're going to become increasingly reliant on technologies which are kind of getting further and further out of our control. And it's this idea that there's the real potential for harm. Now, if something's too good to be true, then you are the product. You've heard that kind of saying. Now, the so-called Magnificent Seven companies are the ones driving the newest forms of strong AI. And we're using this stuff, but like many others, we're worried about the lack of transparency. Any of the open large language models that we have access to they don't perform as well. So now we're making these difficult compromises where we could develop technologies which could be great for patients, but they're costly, and we really don't know what's going on. So how do we do things differently? Now, this is not going to be a simple thing to work out, and it's not something that one particular research group or even country should do. So because of that, we have launched an initiative called the Demon Network, which aims to bring together the global community with an interest in data science and AI to try and tackle these thorny issues. And with funding from Alzheimer's Research UK, the EPSRC, the MRC, and others, and many partnerships, we've built something up which is now quite a large global community with over 1,600 members, and many of the leadership team are here today. So this is a free-to-join global initiative. People can get involved. Organizations and companies can partner with us if they're interested in tapping into the kind of innovation and resource that we can provide. I'd love to continue those conversations. It is truly global. We probably have a slight UK bias, but most of our members are outside of the UK. And as one example of something that we've done, which has gone well, we managed to collaborate with people we'd never worked with before, over 90 international authors, to provide a state of the science overview, a special issue of Alzheimer's and dementia, which really goes into quite a lot of detail about the potential of AI and how AI might make things better, or how we might be able to use AI, and also how AI might make things worse. So, of course, dementia research is behind other better funded fields. We already knew that. And we're all agreed that we need to innovate and tackle complexity and think about innovation. Now, the real concern here is that in our rush to innovate, we make a really bad job of it. And many of the publications that we are out there in the public domain are misleading at best, but harmful at worst. And these kind of models are going to serve very specific groups, much more than others. And increasingly, they're going to serve the interests of very large companies producing the foundational technologies that we are going to become completely reliant on. So we talk about responsible AI, but I think it's our responsibility to talk about irresponsible AI and how things can go wrong. So let's work together and do things differently, and let's tackle things head on in a collaborative way. So thank you very much.
Great introductions by David and Aya earlier about AI, more generally the challenges we are seeing in healthcare applications and kind of like regulatory requirements we all need to face. I'm gonna go quite deep in one specific application that we have in terms of neuroimaging applications in clinical trials, and show you a couple of examples we're working through and how we approach AI development to try and improve neuroimaging measurements for clinical trials. So I'll give a brief introduction to IXICO as a company. So we are a full-service imaging CRO, which means we have all the operational services to collect imaging data from global clinical trials, qualify those sites for harmonized data collection for MRI and PET data, we're focused on CNS exclusively, so we have in-house therapeutic experts in those areas we work in. And then the focus of today is on the analytics, so we have in-house AI teams working on developing contextualized biomarkers for those imaging data that we collect. We've been around for around 20 years now, founded from academics at London universities, UCL, KCL, and Imperial, really with a vision to translate academic imaging solutions into clinical trial applications. You see here how we over the years went from initially a focus on Alzheimer's actually into Huntington's disease and then other therapeutic indications. Huntington's and Alzheimer's are the two areas I'll give some case studies on today. So what we provide to our pharma sponsors really is measurements for drug safety, patient eligibility, and drug efficacy. Most typically for phase 1 to phase 3 clinical development, even though we have done some post-market assessment as well. Where it comes to AI analytics or automated analysis more generally, that's primarily focused on the eligibility and the drug efficacy aspect, whereas safety, as it stands today, is primarily done through visual inspection by trained experts. As we talk about AI, it's quite important to reflect maybe on this application insofar that it's a reasonably controlled environment, insofar that the data collection is very controlled, the data flows is very controlled in a clinical trial compared to like a true healthcare application. We have QC steps along the way. We have the ability for manual intervention if there are issues with the automated assessment. So these are quite useful environment to obviously develop new tools and then test them in that environment. And it's quite different to like an open healthcare environment where you have different time requirements in terms of real-time analysis, and you also don't have the controlled environment of a clinical trial. As I said, we're quite focused on translating and developing novel technologies, so we maintain our network of academic partnerships, including Dementia's platform UK here, of course, and then we work in other initiatives across the therapeutic indications that we serve. So with that, I'll spend just a couple of minutes briefly reflecting on how we use AI and how we do the method development in our space. So for us, as I said, it really comes down to making subject level decisions, specifically when we talk about patient eligibility, where we really require high accuracy in every case. We don't necessarily need a tool that is generalizable to all kinds of populations and therapeutic indications. So that can be quite focused on a specific application, but it needs to be highly accurate in that case. As I said, we can operationalize manual intervention, but that needs to be kept to a minimum, both for operational reasons, but then also to reduce bias as much as possible. When we look at training and develop those models, we think of it at different levels. That applies to the type of data sets we use. So David just now mentioned ATNI, for example, which of course is a widely used data set and which is large and available, but it comes with its caveats in terms of the fact that it's one data set, it's quite specific. But that, again, there's potentially less contextualization available in the data set, but it serves well to perform some let's say, high-level training in terms of, let's say, brain segmentation, which is one of our key applications. But then what we do for a specific application, when we look, let's say, at a specific brain region in a specific therapeutic indications, we would be further optimizing those models with typically smaller data sets. It may come from a clinical trial where we have the R&D rights to use the data, and where we spend more time on the contextualization, which in this case would be the manual segmentation. And then with that, we have our general approach that in terms of the pre-processing and potentially the neural network architecture, or even the high-level training, when we think about transfer learning, that is some kind of base model that is built on those larger amounts of data sets, and then fine-tuning we would do as we go into a specific application in a specific domain. And similar to, I think, some of the points that David made in the previous talk, for us it's often not about the biggest data set, it's more about the right data for the right application, and with the right manual annotations for training. With that, we have, around a couple of years ago, we've started transitioning our base technology for automated brain segmentation from a multi-atlas based approach, which essentially uses a large manually annotated data set to then duplicate those segmentations in an unseen data, to a framework based on neural networks that we call IXICO.ai, and again, that we would then customize and optimize for a specific application. We've presented, for example, so Richard, who's here, who's our head of R&D, presented last year on that model using for hippocampal subfield segmentations, and I'll show some other examples in the presentation here. And that actually gets us right into the first case study, which is in Huntington's, which is obviously not the focus of this meeting here, but I thought illustrates well the kind of steps we go through, and kind of like the same questions we're facing in AD and other indications. So other than in Huntington's, there's no not a very specific biomarker available in Huntington's disease when we compare to Alzheimer's disease. And in a recently proposed staging framework on the biological definition of the disease, volumetric, so brain volumetry in the striatum, so the caudate, the putamen, is playing a key role in terms of the staging of the disease. And then obviously is a good measurement both for patient eligibility and drug efficacy, which are two of the key applications I mentioned at the beginning. There's a staging system that is being proposed that our sponsors are increasingly interested in adopting, in terms of selecting a more well-defined subpopulation. And the challenges we're facing here is really, okay, so how can we have a reliable analysis of those brain regions so it can serve as a robust and reliable input into screening into those trials. And then the other thing on the efficacy analysis, where you potentially have a bit more room in terms of the accuracy because of the statistical effects by looking across the whole trial. But again, it's an important area to improve the accuracy, specifically as there's increasing discussions for consideration of those measurements as a potential surrogate in Huntington's. So I'll briefly show how some results from the adaptation of the IXICO platform I've shown earlier for putamen segmentation here, which is one of the key brain regions relevant there. We have a specific sponsor project where this is used for patient selection which is also linked to the fact it's a gene therapy where they administer into the striatum. So they really need high accuracy segmentation of those brain regions. We are able to manually, QC those segmentations and annotate them where needed. But if you have severe missegmentations to start with, then that's sometimes difficult to impossible to recover. So again, we used our base model for brain segmentation and then optimized and trained it specifically for that application of putamen segmentation. And what we're looking at here is some of the results, and I'll walk you through this. We're comparing to FreeSurfer here, which is one of the most widely used brain segmentation, but it's a general tool. It basically gives you 150 brain regions, and they all look good at some level, but aren't focused on that specific application. We're also comparing against LEAP here, which is our in-house multi-atlas segmentation approach. And again, we see the same effect in that if we use just a general model of that technology, which gives you good segmentation across the whole brain, but isn't optimized for specific region, we don't see good agreement with the expert annotation. We can optimize the LEAP platform as well to focus on specific subregions by basically optimizing how atlases are selected and how we define the segmentation. And that helps improve that here to a similar level what we see with the IXICO.ai platform. It's a much more involved, much more cumbersome, much more complex process, but it essentially gives you a similar result, which just demonstrates how using the right data in the training can improve here. If we use those more general tools like non-optimized LEAP or FreeSurfer, we see significant differences. We see like a dice overlap, which is the basically overlap between the manual and the automated segmentation, where we see good performance for the two optimized method and then low performance for the more general methods. We did another study with the UCL team, UCL Huntington's team with Sarah Taprisi, where they visually QC'd the data that came out of the CNN platform and FreeSurfer. And again, you see significant improvement in terms of quality failures and then the quality you get with the AI method. So that's a good starting point. But as obviously we know, and as was discussed in the previous talks, we really need to validate those tools so they become ready for prime time. There's a lots of questions. If we go with this kind of data to our sponsors, they will want to see more detailed application and specifically their patient populations and independent data sets. They have concerns about the regulatory data they need to go, or the validation data they would need to have their discussions with the FDA and so on. So what we've done with a couple of pharma sponsors as well as the CHDI Foundation in this instance, and I think again demonstrates or shows what kind of steps we need to go through as we develop those methods in a more academic environment and then get them ready for prime time, so to speak. And in our case, that's still not the real world, I would say, because it's that controlled clinical trial environment, but still we need to cross-validate and look at larger data sets before we have the confidence that we can roll them out more generally. So we partnered with the CHDI Foundation to put that technology into a large data set of more than 6,000 imaging across Huntington's and healthy subjects, spanning across a range of natural history studies as broken down here. Some of you, if you work in Huntington's, are well familiar with those. Some of the data is actually collected here in London at UCL. And there's significant interest from our pharma partners to partner in those projects. So we have currently 3 sponsors contributing funds and expertise into this project, because that is really the data they need to then inform their trial planning. Some of the applications people are looking at, of course, are listed here. So we talk about power calculations as we're planning the trial, but then I mentioned patient selection or enrichment as we are staging subjects. There's the more advanced disease modeling concepts, which goes towards power calculation, I guess, in some way, but where you add additional variables that are available in those data sets. And then finally, evidence as part of the regulatory engagement to deploy those endpoints. These volumetric endpoints in Huntington's typically are secondary endpoints, but they are moves towards potentially promoting them or giving them more power in terms of potential surrogacy. And then as we have less natural history data in this indication than in Huntington and Alzheimer's, obviously there's quite some interest in looking at those kind of data sets as an external control arm. Just before I move into Alzheimer's, this project is running, so we're kind of like halfway into the analysis of the 6,000 data sets, and we start seeing how that helps the partners here. Unicure, who's the founding member of the consortium, is starting to publish data. We see that in their press releases, in their more scientific engagement, where they start using the data both for trial planning as well as for patient selection, which obviously is what the intention was here. And then we have next steps lined up where we, with the CPAF consortia in Huntington's in this case, of course, we are starting regulatory engagements with the FDA in particular to get a better understanding of where this additional data puts us in terms of the requirements to better understand those endpoints. And with that, I'll go to the second case study we have, which is in Alzheimer's disease. As we all know, we have much more established biomarkers in Alzheimer's, specifically with amyloid, of course, which is an integral part of the biological definition for the past 10 years, systematically deployed across trials in terms of an inclusion criteria. It plays a key role for efficacy, specifically in amyloid, targeting therapy. We've seen initially, maybe as a surprise to some, but now that it was kind of like post hoc considered like a surrogacy biomarker of reasonable likelihood in the Aduhelm accelerated approval some time ago, but now it is a key part of the Leqembi approval as well. And more recently, we see it being firmly integrated, at least into the updated draft guidance we see coming out from the FDA. So it's an important part, and amyloid PET obviously is one of the measurements besides CSF that are established. But we see blood-based biomarkers, lots of discussions yesterday and at every meeting for Alzheimer's, of course. So what I'll touch on a little bit in the next couple of slides is just some open questions we're trying to look into in terms of amyloid PET analysis in AD trials in particular. There's this open question on how you deal with the visual read versus quantitative analysis. We have well-established analysis approaches now for quantitative analysis in terms of global cortical SUVR, for example. But then the gold standard and what is on the label of the tracers is a visual interpretation. And obviously, those can disagree in some cases, and that's an interesting area to look at. Those of you who are familiar with the AMI-PET consortium, which is one of the partnership consortia we had on the earlier slide, that consortium has just initiated an interaction with the European Medicines Agency around quantitative analysis on PET for you know, for definition of status, amyloid positive or negative. Another area that came up a couple of times during the meeting here, and of course is an important topic in the field, is the inclusion of more diverse populations into AD clinical trials. And I'll show some results we're working on in terms of, are there any differences? What does it mean for the PET measurement? Can we compare like for like across those populations? Is there any requirements to change read criteria and so on? And then finally, before I close, I briefly touch on the project we're starting, where we're looking at how we can best integrate the what we surely will get from a blood-based measurement with an imaging assessment. So there's two projects I'll focus on. I'd like to signpost to two of my colleagues here, so I'll talk about the GAP BioHermes partnership a little bit, and Lynn Hughes, who's here, will present on that study in more detail later this afternoon. So I'd like to point to that here. And then the second project I'll focus on, or I'll briefly mention at least, is led by my colleague Richard Jules, who I've mentioned earlier, who again is here all day and is leading that project. So the GAP BioHermes study, I don't want to preempt Lynn's talk in any way, so I'll just give a very initial introduction. But this was a study designed to evaluate the ability of blood-based and digital biomarkers to reflect the presence of brain amyloid in participants enrolled in AD clinical trials. We as IXICO, we've done the PET imaging on the study, and that's what I'll focus on. I'm sure Lynn will give more detail on the blood-based and the digital biomarkers in her presentation later. A key secondary objective of BioHermes was to include a significant representation of ethnic and racial minority participants, which the study has successfully done, in that it recruited 24% of traditionally underrepresented participants into a group of around 1,000 subjects. I'll talk a little bit about some initial PET findings, specifically as you compare that across the different racial groups here. And I'd like to focus on the comparison between the white and the Black or African American non-Hispanic groups. So you see 727 and 103 subjects in those groups respectively. Slightly younger participants in the Black or African American group, and significantly higher female proportion. I'm not showing those results, but we did do some quite detailed investigation to see if that's driving any differences, and it's not, which is worth pointing out. Slightly lower levels of education, but still high levels of education in the Black group compared to the white group. And then interestingly, lower MMSE levels, similar APOE4 carrier status. And then the key finding at the bottom here is those significantly lower levels of amyloid positivity in the Black or African American group compared to the white group, where at the same time we see a very similar average SUVR. And there's, of course, various hypotheses to these. I've presented those results at the CTAD conference in last autumn. And these are basically the questions that came up in the discussion there, and there's some of the key questions we're now trying to get answers to. But so what the results? So what this disagreement between the amyloid visual read and SUVR findings basically mean is so the radiologist basically scores those two subject groups differently in some sense, but then the average SUVR is still similar. So what does that mean? Does that mean that we have local differences that explain why there's differences in positivity but still get the same average SUVR or similar SUVR? That's one hypothesis we're trying to look into. there was one question that was raised, whether, again, when I presented this, does it mean our visual read criteria are not suitable across populations? I think that's a strong statement that I don't necessarily think we have evidence to back up, but we definitely need to investigate. I think another hypothesis that we need to look at further is if there are any systematic difference between those two groups in terms of comorbidities, whether there are differences in socioeconomic status, for example, that then lead to different levels of vascular pathology, which may also explain the fact that we see similar levels of cognitive impairment, but then different levels of amyloid positivity. And these are the questions we're working through. We presented some additional results on that at the HAI conference earlier this year. And what we see on this plot is the SUVR, so the quantitative PET assessment plotted per visual read group. So basically we have for the Black, African American, and the white groups separately plotted the A beta negative per visual read and A beta positive, and then for both of those groups the SUVR. And what we also see is the percentages on agreement and disagreement. So if we start with the A beta positive groups for both racial subgroups, we see 93% agreement between the visual read and a cutoff of 1.1 on amyloid PET, which is an established cutoff that is widely used, and that's the same in the white and the Black groups. However, if we look at the amyloid negative groups, and if we start with the white, again we see 87% agreement that those are amyloid negative, 13% disagreement, and that's significantly different in the Black or African American group. So what it basically means is that in that population, there's an increasing number of subjects where the radiologist rates someone amyloid negative based on the established visual read criteria, even though the SUVR is elevated on average. So that's something that we're looking at further. We have an abstract actually accepted at AIC, so we'll present more at that upcoming conferences where we're specifically looking at whether there are differences in local uptake patterns. So again, as I said earlier, while we're seeing elevated average SUVR, but the radiologist rates those subjects as negative, how does that link to where we see this uptake is essentially the underlying question. And then that's just some preliminary work, again, Richard is working on, where we now try to, okay, is there anything more data-driven? Can we use AI to help better understand why we see these population differences or potentially confirm there are no differences? So a quick experiment we've done here is to, if we classify A beta status based on the SUVR, so a regional assessment of amyloid uptake, we get to an accuracy of 89%. If we use a deep learning model here in this experiment, we get to 93, so I would say that's not a big difference, and we know there's lots of caveats around the deep learning model. I think the more interesting finding here is that if we train the AI model on a white population and apply it to a Black population and vice versa, we don't see a difference in terms of performance, which does suggest that patterns trained on one cohort apply well to the other cohort. But that's just some very preliminary work. What we need to, or what we're looking at now is to better understand which brain regions are actually driving the AI prediction. Does that link to the visual read criteria in any way? How does it compare to the global cortical average SUVR we're seeing? And then, yeah, try to understand those points better. And I'm conscious of time, but this is actually going into my last slide, and it's literally just a brief sneak preview on a new project that, as I said, Richard has started to initiate. It's unfortunately, it's about to be externally or publicly announced, so I can't go into too much detail and name it, but it's with a UK consortium here where we're looking at, just from a technology point of view, so how can we integrate blood-based biomarkers with imaging, or how can imaging support a workflow where most typically where we would all expect a blood-based biomarker to be used early on in the screening process in a diagnostic application, and then where's the complementary value? So this is my last slide. If we look at this, starting on the left, if we look at a potential diagnostic workup, we probably everyone agrees that we will have some kind of plasma assay pretty early on. But a big discussion is how do we deal with cases where there's an ambiguous or there's a not clear answer from the plasma assay. So this would basically be then routing into the PET scan here as a confirmatory analysis, and we're doing some work to understand, you know, what cutoffs for which blood-based biomarkers might require that additional assessment. And then the other part of the project is to integrate that with MRI imaging to look at the differential diagnosis aspect, so quantify vascular pathology that may contribute to an inconclusive plasma finding based on a given clinical observation, and then can also help differentiate against, for example, FTD or other types of dementia. So that's work in progress. Again, I hope that's worth briefly mentioning, and we'll be giving more updates on that in the future. Richard is around all day. If you want to discuss that in more detail, I'm sure he's happy to dive into it. And with that, I'll finish. Thank you.
Hi, thank you for your wonderful presentation. Actually, my question is about the amyloid biomarker and the tau biomarker of PET scan. I have recently started my PhD in this January, and my research topic is early detection of dementia using AI from neuroimaging biomarkers or neuroimaging. So from the studies, I have found that amyloid biomarker, actually in the healthy aging brains, amyloid biomarker can develop, or amyloid protein can develop. So in most of the studies, they have demonstrated that maybe tau biomarker is better than the amyloid biomarker for detection of the or prediction of the dementia. So I wanted to know about this, if you have any research or any kind of work is going on in using tau biomarker.
Yes, I think we need to look at the time domain here, where, because amyloid, and if you look at the ATN model that I'm sure you're familiar with in terms of the definition of the disease into amyloid, tau, and the neurodegeneration, and you know, the infamous cliff check curves that I omitted from the talk, but we usually see in these kind of talks, is where you see that amyloid plateaus pretty early on, way before we see clinical symptoms. So that can be 10 years, 20 years before we see clinical symptoms. And then tau serves more as a staging biomarker, or as a measurement of proximity to disease, where you basically see spreading of tau much more closely to onset of clinical symptoms. So that's potentially where you're coming from in terms of the importance, I think, to give a diagnosis of Alzheimer's or to recruit into a trial. Amyloid is critical because it shows the presence of the disease. But then as we talk about staging of the disease, tau is important, which is why, for example, the donanemab trial that Lilly ran, where they looked at a specific range of tau deposition to be eligible for the trial, so to really narrow down the stage of the disease the subjects are in. So is that helpful? Okay.
Okay, Robin, thank you very much for that talk. One of the distinctives of this conference is the interface between industry and academia, which we value very highly. So I'd like to ask you, at what point is it of benefit to a company for your proprietary data and your algorithms to be made publicly available?
Yes. So I think, well, generally we want to support science, right? It's in our interest to support the field, and but then obviously we have our commercial interests as well. So I think we do work in pre-competitive consortia. I mentioned the HD one. So that data will become that data is held within the project partners for a period of time, and then will become publicly available, so everyone can use it. It's actually free to use for academic use from the beginning. And we, for example, we also work in other CPAF consortia. I mentioned the HD one, but work in CPAD as well, and Alzheimer's, where we provide our analysis. So we don't have our own data. I mean, I think maybe that's one thing to clarify. We don't run our own trials. We don't collect our own data. So for us, it's more providing our analytics into existing data sets. And that, I think, we have a vested interest. We want to validate the pipeline further. So we're very happy to discuss whether there's any data sets you have where it's worth running those algorithms, and we can make those available. The gap data that I've mentioned as well is available under GAP's terms, of course, but that includes the analysis we have provided.
So thank you very much.
Thank you.
Yeah, we decided to do this presentation as a duo. You know, it's going to be kind of interesting that way. But yeah, I'm Ben. I'm a biopharmaceutical PhD student. So this isn't actually my field of expertise. But I started doing this project about 4 years ago, just basically voluntary. And what we're interested in is basically identifying sleep variables and looking at the interaction between sleep and dementia. One of the biggest challenges of this, as I'll explain a bit later, is actually harmonizing the data. So without further ado, I'll let Uli explain some of the nuances of sleep for maybe a sentence or two. Or
Yes, so hi everyone. So I'm the one who's responsible for making Ben spending his free time on analyzing data in the DPUK platform. So I thought I'd say 2 words, basically briefly about sleep and the importance of sleep. And I think you may have noticed that I'm interested in sleep already by the questions that I asked yesterday. But here I am again, just to let you know that I just want to say 3 things about sleep. That sleep is important for good health, basically. And we know that sleep is crucially involved in sort of molecular, immune pathways and other pathways that include neural function, which contribute to healthy development and aging, but also it goes awry when we're not healthy anymore. We know that sleep goes bad, and occasionally it can be an early indicator of things going bad, I think. So that's evident in people with mental health problems, for example, but also in dementia. Sleep is a risk factor, but also possibly mechanistically linked to dementia and neurodegeneration, where some recent evidence points to the fact that sleep may have a role in clearing out waste during sleep and sort of removing some of that protein debris that we see build up in people with neurodegeneration, and sleep may have an active role in removing this debris from the brain. But I'll leave it there. Basically, this whole project came out of a analysis project during a datathon, basically. So Sarah and I, I took part in one of the datathons. Ben was there, and we worked together for a few weeks on this project, and then decided to go further because we found some interesting data. And essentially, we thought that the assessment of sleep within the DPUK platform was maybe not ideal. So we thought, how can we find data that is related to sleep, and how can we relate the sleep characteristics that we find that then to cognitive function and aging and neurodegeneration? And we sort of identified, slightly naive, maybe 20 or so cohorts that had sleep data, and we thought we could go on and characterize this data basically, and quickly hit a snag, I guess, and we were slightly overwhelmed by the complexity of the data. But then Ben came in with some really innovative ideas of how we can approach the complexity of the data and find better ways of finding data within the platform. And this is the rest of the talk, so I'm going to hand over to Ben, and he'll tell you all about this. So.
Cool, yeah. as Uli mentioned, we kind of got overwhelmed with the data. So firstly, we went on the Dementia Platforms UK. I think there were 53 cohorts at the time, but now I've just read the pamphlet and there's like 63, so it keeps growing. When we extracted that, we had a look at the metadata just to see, okay, well, how much data is there out there? And there's basically over 86,000 variables. So simply putting in Control F, sleep, is not really going to work. There's like a lot of different things. I'm not an expert in sleep either, so I didn't really know what actigraphy or all these things are. So I had to refer to another corpus of intelligence, which is basically the UMLS, or the Unified Medical Sleep Dictionary. So yeah, summary of this, data is hugely heterogeneous, and it's big, a lot of participants. I mean, I think we estimated over 200,000 participants across all these studies. So yeah, as I mentioned before, the UMLS, it's basically a meta-thesaurus, and it links everything together. And the way we sort of envisioned this is that we want to reduce how many variables that we're dealing with. So it's kind of like a funneling system where we put in a cohort, we're matching it to this meta-thesaurus, and we're using these ranking or filtering procedures, and then attaching those newly matched variables and using them as a reference. So it's kind of a feedback loop that's going round and round. So yep, an example of basically a very specific example of how we're doing this. We were basically looking at cosine similarity, which I think some people might be familiar with. We had a look at Levenstein distance, fuzzy matching, word embeddings, semantic networks, but often what we find is with the restriction to the internet access on the DPUK, it's quite difficult, and there's kind of a necessity for something a lot simpler. So we came up with this system where we're scoring things from 0 to 1, 1 being a perfect match, 0 being a pretty bad match, and we're just looking at what's a good way of like filtering down these and funneling these down so that we can select them manually. So it's a semi-manual curated approach where we're looking at cosine rankings and then matching them, using those correct matches to bulk our data, and then going cohort by cohort and getting bigger and bigger data. And the results of that, yeah, we've identified over 700 unique sleep variables. The most common metrics were basically sleep duration and quality. There's some other scores that you can have, like the Epworth sleep score and all sorts of other things, but generally the one that's harmonized across all data sets is duration and quality. We used these in a subsequent study by another colleague of ours, Penny, and I implore everyone to have a look at these posters. We've got 2 of them up, and basically one summarizing what I've said today, the methods, and I think this is quite useful for everyone involved as well. If you've got some sort of niche research and you want to like whittle down that data and funnel it and really hone it in, using a strategy like ours seems to work and saves you a lot of time. And the other one by Penny is going to go into some of the sleep duration analysis that we've done. So, yep, I hope I didn't go over time. I probably did, but many thanks to all our collaborators, especially Sarah at DPUK, Penny, who's been the bulk driver of the sleep duration analysis, and obviously Uli as well for the sleep expertise. So yeah, many thanks.
I'm all about big data, and how it can be used to help patients. So I'm going to present a really very flash talk about some really new research that we've been doing within our team, and I welcome any feedback because it's quite new. So if we first of all go on about side effects. So side effects are unwanted and undesirable effects associated with a drug. And the problem is they can come from very minor, so a sniffle or a cough, all the way to the extreme, so heart attacks and strokes. Now, the problem is that as you have side effects, you can increase your risk of hospitalization and also increase your risk of death. And this is very paramount for those people who are aging, so the older populations, and also those living with dementia. So it's really, really important to understand and to find any undesirable side effects associated with drug treatments. So we could use clinical trials, and they are really good at detecting side effects or safety of medications like brain swelling, for example. And this is also where big data comes in. We are looking at a whole population of people. It's more diverse. We're looking at everyone. And they're also very good at detecting the rarer side effects. So how can we actually utilize big data to find out more about dementia treatments and their side effects? So the method that we're introducing is called sequence symmetry analysis, and it's a signal detection method to detect side effects of drugs. And it basically is a very computationally efficient, it's very quick. All you need is information about the date of your first drug and the date of your adverse event or your drug that you can be used as a proxy for that. And basically, in very simple terms, it looks at the symmetry of the sequence of when you take one drug and when you take another. So I always find that we do pictures because it describes things better. So if we think about the vertical line is when somebody is prescribed a dementia treatment, and we want to understand if nausea is a side effect of these dementia treatments, we can look before and after and see when each person, if they're prescribed an antiemetic, which is used for nausea, if it's before or after. Now, the way that the symmetry comes into is if we're looking for nausea and it's not an adverse effect, it's not a side effect, what we'll see is the people who are prescribed the antiemetic before our dementia treatment should be around the same number of people who are prescribed it afterwards. And what we see here is it's symmetrical. And what we can do is we can take the number of people in red, divide it by the number of people in the yellow, and we get this sequence ratio. And we can adjust for prescribing trends in this in order to take that into account to not bias our results. However, if nausea is a side effect, then what we see is that after the dementia treatment, there's an increase in antiemetic prescriptions afterwards. And for all the causality police out there, I know I've put cause in there, but what I wanted to put in there is increased probability of an association, but that's too much to put on a slide. So what we get in that sense is we get an adjusted sequence ratio greater than 1. So how did we use this for dementia treatments? So we went on the NICE website and the European medical catalogue, and we picked a couple of side effects that we could proxy using drugs. So we used antiemetics that are used to treat nausea, anti-epileptics for seizures, antipropulsants for gastrointestinal problems, and then psycholeptics for agitation, aggression, and psychosis. And then we perform this analysis. So what you can see here is any circle that's in a thick black line is one that's got an adjusted sequence ratio greater than 1, and that could potentially indicate that these are side effects proxied by the drugs with the dementia treatments. And when I say dementia treatments, I mean acetylchlorinase inhibitors. So from the top, we can see that the antiemetics are potentially being used to treat nausea, which is a common side effect. The other ones with the anti-epileptics and the psycholeptics, they're a bit more interesting because although they imply here that these drugs are being used to treat the side effects of the dementia treatments, they are also themselves a part of the disease progression process. So what we need to do is do some additional sensitivity analysis to kind of look at the different time windows to see if we still get the results that we see. And then for antipropulsants, we see a nice adjusted sequence ratio greater than 1. So what I've kind of done very, very quickly is shown how big data can be used to detect known side effects related to dementia treatments. But the value in big data now is how we can use it to define unknown side effects. So currently at the moment, I am 600 out of 900 drug classes running through all of the different drug classes across medications in our database. And what this shows is that we can also use this method and apply it to detect these unknown side effects. And we're also in the process of looking at Parkinson's treatments and also drug-induced Parkinsonism. So no work is ever just one person. It takes a village to do these sorts of things. And so I'm really lucky to work in a really good team with data scientists, code developers, clinicians, who make this work possible. So with that, I thank them and also my funders and you for your attention.
Hi, I guess it's a question for David up here. David, I was interested in your comparison between logistic regression and AI models for prediction of dementia, right? The graph that you showed. We've done something a bit similar where we compared logistic regression to AI to predict essentially ATN status in people who are cognitively healthy. And what we found was that logistic regression is pretty optimized for Alzheimer's disease pathology, right? And that's probably, to my mind, it's logical because we know a lot about what predicts Alzheimer's disease pathology. But AI seemed to be picking up a lot of the non-Alzheimer's disease pathology. So basically, negative amyloid, but positive tau, and positive neurodegeneration. So I guess I wondered what your thoughts were on where AI sits specifically, sort of moving the needle beyond just thinking about predicting Alzheimer's or detecting Alzheimer's and going for non-AD pathologies. Have you had any experience in that?
Thanks, Ivan. Yeah, I wasn't joking when I said that logistic regression can actually be quite powerful. But it's only really good at linear combinations of pretty clear associations, and it is modeling the unique contribution of those. Now you can manually force that kind of regression-based model to look at interactions, but it's not very effective, and it's a little bit clunky. Where other types of machine learning can be more powerful is where there are genuine interactions, particularly if you think that there's some kind of biological plausibility to that, or it's sufficiently complex that the model itself needs to learn from its mistakes. So things like extreme gradient boosting can go back, and it can, because it's labeled data, you know what the gold standard outcome is, and you can iterate and learn. But that's not always necessary either. So I thought, it's very, I got some flack on Twitter or X, publishing where we didn't just use the boundary of what machine learning is very fuzzy. But someone said logistic regression, that's what you're doing at the Turing Institute now, is it? As a way of putting it down. And I was like, no, this is good science. You don't need to unnecessarily complicate things, and you should benchmark against the simplest appropriate method, because that might be enough. So where you start looking at dementia subtypes with more complex presentations, or the sample size is simply smaller, that's when the different approaches can come into their own. Things like random forests are very nice because it's averaging across models. So with smaller data sets, it's actually a little bit less susceptible to overfitting. So, outer sample performance is what we're really all interested in, not, the kind of, we've got an ROC curve of this. Who cares?
Thank you. Any other questions? No? Perhaps I could ask one of Ira. Through your talk, there was a very strong theme that there was a lack of clinical implementation, and you touched on things like clinicians learning mathematics, and you touched on the government getting behind this. And in the UK, I think there's a real cultural difference between clinicians on the coalface and academia. But I wonder what we could do to address this in real terms, and how long it might take to kind of make that change so that we can actually implement these algorithms into the NHS.
I personally think what it needs to show efficiency and to show convincing results. And that means that the algorithm needs to come to the family practitioner, there where it would really help and solve the problems, identifying in diagnostics the situations when the doctor is struggling and does not know. But to come there, we as a community have to agree on standards. And for example, how should a patient and a doctor be secured that the right method has been chosen, that the right prediction is done, and especially, as I mentioned before, what is happening when the algorithm is predicting wrongly. So this has to be solved, and an intellectual concept has to be delivered very quickly. Because it's needed, as I during the break stressed, 49% of our world's population is soon living in Africa, and 0.3 MRI machines are available for 100 per 100,000 people. There will be no PET.
Sure.
Yeah.
Thank you. Next question.
Thank you. I really enjoyed your talk, Ira. And I was struck by two things. The first thing is that you suggested that medical trained people should perhaps do some more maths, which is a bit of quite an ask, I would say. The alternative that I had in mind is that if you develop any AI method, shouldn't you be able to deconvolute the data or whatever, that you can discuss the performance with medical trained people or epidemiological people or whatever experts there are in a way that they can help you evaluate whether you have fallen in a trap. Now, I myself as a geneticist have been looking at neural networks that was using missing data to predict things, and I'm still puzzled about that. But I think that that should be the level also that AI should perform. You should be able to show me what the model is using and whether it makes sense or whether it has fallen in a trap that the medical person can tell you.
Well,
a microphone each.
That's preferable, but we are going to be forced with a trade-off for some questions that are only be solvable by very complex models that are going to be very hard to communicate. So I don't just mean the transparency and the black box nature of some models. I just mean even the very idea of how the model works. We need to be really brutally honest with ourselves as to whether the performance justifies the additional complexity. I think with most things in our lives, we are perfectly happy to use things that we don't understand. You know, I don't understand in great detail how a smartphone works, but I feel a bit lost without it though. And I think there's almost the danger that we're going to end up with that kind of situation with some of these models that we like using them. They're perhaps the ethical thing to do may be to use them, but to look under the hood and truly understand that maybe too much of an ask for an average clinician, for example. You know, you don't insist on that for all other technologies. I mean, like MRI scanners and so on, like most clinicians are happy to use the resulting outputs from that and trust that if it's appropriately regulated, they personally don't necessarily need to understand every aspect of the physics.
Can I reflect on that? Because I know my phone, if I open my email on my phone, it shows the same as on my Windows PC, right? So I don't think you need to understand the model completely, but let me give an example how we, for instance, pick this up, is you simply ask SHEP values and then you show, oh God, all of a sudden the missing values predict instead of anything else. Another example, we made a metabolomic clock and we thought, gosh, why are omega-3 fatty acids, which supposed to be the dream of any nutritionist, that we should eat them as much as possible to protect our brain and more. Why are they associated with an increased risk of aging, for instance? That doesn't make sense. And at that level, you don't have to understand the full model. You just get the pointers with a simple SHEP value that point you to there's something odd that happened.
Thank you. Do you want to make a comment? And then there's a question
short
over there.
comment. I think you are very right, and no car would be launched onto the market without criticality assessment, and that is just what AI algorithm in medicine also need. And it is our community, which should demand the criticality assessment criteria. And the criteria are liability, claim rights, and so on and so on. So that should be clear.
Fantastic.
Thanks. Another question for David, and a statistical one. Just extrapolating the logistic regression one and a sort of binary moving ordinal, because I think a lot of us are more interested not just in dementia, but the progression. So we're using scales like CDR or one we've developed, which is the DSM-5 scale. So we're dealing with ordinal data. Now, when we compare ordinal logistic regression with a whole variety of AI models, they have awful AUCs compared to binary. You know, it's much easier to guess yes, no than what is the scale out of 7 points. But actually, none of the AI ones do as well as OLR. And I don't know how we deal with that, because clinically, I think we want to know how people progress up the mountain, if you like, rather than just they suddenly went on a cable car from the bottom to the top in 5 minutes. Do you have any solutions for that, statistically?
You're right that ordinal scales are more challenging. You get the threshold wrong with binary variables, but it's not that damaging if the groups are fairly well spread in terms of performance and so on. The problem is that the ordinal, you have to question whether the ordinal scales are a good representation of the underlying processes, or whether they're a convenience, you know. So things like CDR staging, I think it is useful, but when you look at the actual trajectories in the cognitive data and so on, it looks all a bit more continuous. So it's difficult. There's nothing wrong with using those, you know, there's nothing wrong with using the simplest models available. It is disappointing that some of the models are just so prone to overfitting. I think that's the problem with the ordinal data. But there are ways in which we're learning to try and kind of almost work around that. But ultimately, it just may be the wrong approach, you know, and I have no problem with that. Like sometimes, we've seen that with genome-wide data as well. Sometimes it performs worse than regression-based models, you know, and just hold our hands up and go, well, that's the best model that we have. Maybe we can invent something that will perform better in the future, but that's why I'm so keen on these head-to-head comparisons, because there's a lot more honesty about it. And then we don't have a false dichotomy between traditional statistics and AI. You know how we want to badge it? It's modeling, and there are varying degrees of complexity with different trade-offs, and that's fine, right?
Okay, we've got time for one more question before we hear from Danielle. Any at the back? Sorry, yeah.
Thank you for organizing the event. So my question is for Ira. So you mentioned about the lack of availability of data, high quality data, and which is also diverse in terms of socio-economic background and ethnicity. And also you mentioned about the standardization of the data, how we collect it. So my question is, what's the barrier to get those high quality data? And how to overcome those barriers?
I guess that the medical profession is changing, and it is demanded from more engineering, also in the attitude towards your profession. And the intuitive medical doctor is not in that amount of people any longer the average doctor. The accuracy of the work done by a doctor or a nurse or whomever would be collecting data needs to be increased. There is too much intervariability, and a lack of strict procedure following. And the modern data-driven analytics is demanding engineering. And this will change a profession. And and this is always difficult. The doctors have to change their attitude to collect data. And this is a very sensitive issue. Yeah.
Yeah, and how about the diversity of the data? So having data from various socioeconomic background and various ethnicities. So how to overcome that?
I didn't understand your last question because of
the diversity of the data we collect. So the data we have is primarily from white people, right? So if we would like to have data from different ethnicity and different various socioeconomic background, so how can we do that? How can we achieve that?
At the moment, you have standardized procedures and made them more collectible in a standardized way. You can also apply with less human contact, to say it carefully like this. If you have a digitalized procedure like in AI Mind, you can apply it everywhere in a local community. The goal was to produce a method which can be applied by non-professionals.